We're gonna do the first, well, we're gonna do my tutorial first because hopefully a lot of you have produced a successful cosmological simulation. So in that sense, if that's the case, your directory should look now something like this when you submitted the simulation. Did some of you get to this step? Or are there other? Let me ask the other way around. Whose directory doesn't look like this? Should be something like 16 snapshots.
Pretty sure my code timed out at 8 hours.
How many snapshots do you have?
Let me get back on that. I got an email saying my code timed out at 8 hours.
Yeah, unfortunately, it was a little bit. So our nodes are not like equally fast. The ones I use, they do this simulation in 2 hours, 2.5. The older ones, they apparently do it in just about 8 hours. So I thought 8 would be enough. And I think it worked for most of you guys. Oh, yeah, right, you're right. Okay, maybe that's better. If your directory doesn't look like this, it's not a big problem because you can just use the snapshots that are placed in mine for the tutorial. You just maybe have to do some redirecting of like the Jupyter Python notebook that we're gonna use for that. But I think that's only one case that was unlucky. So from most of you guys, I heard like thumbs up for like having 16 snapshots in there. Okay. In that case, you can, if we do that like we did it yesterday, you can just go, you should be able to copy the readsnap3.py. Where's my notebook? Yeah, the Cosmobox IPython notebook. And the g3read.py, I can actually also list them for you. To your directory, and then you should be able to log in based on a notebook. So they showed you how to open a notebook on the cluster, right? But first copy these 3 files. So it's, yeah, give me a second. It's g3read.py, readsnap3.py, and Cosmobox. I can, yeah.
I don't think we have permission for the Jupyter.
You don't?
It works for me.
Ah, okay.
Yeah, we don't have access.
Yeah.
I'm getting permission to not the Python notebook, but the 2.py scripts are working.
Okay, okay. That's weird. Actually, yeah, give me 1 second. I guess the reason for this is that this is all in my home, so. Yeah. But the notebook should also be in here. Can you try to pull the notebook from here? That, on that directory? You typed that pretty quick in. Yeah, that's the directory. I meant, well, what? Why is that on my? Ah, no, that should be myself. That's fine. This looks weird. Did it work for you guys? Yeah, exactly. You got also permission denied. Ah, okay, okay. Yeah, that's actually right. Oh, we can't do it like that. That always works. Okay, try again. Works? Okay. When you done that, start a server on the Jupyter Hub. Here. Let me clear that again. Sorry, this one.
Wait. Oh, from this chat. Okay.
Some of you started a server already on the Jupyter Hub? Okay.
How many cores for the server?
One. No GPU. Yeah, it's in that one. Sorry, can you repeat?
And I think we're all already there. Like,
Yo.
any of us are actually.
Okay, cool.
Or we're still typing. Yeah.
Oh, wait a second. Okay, so you should, if you're already there, you should just go to the directory and open the Jupyter notebook. Maybe that works. No. Just like it should work as is. Like you should just open it and you should just be able to shift enter through that thing. If you did, well, should, you know, it's computers, it never works. Everyone able to see something like this? Okay, did you guys try to execute the first cell? Does first cell works? Okay. Sorry. Okay. There is no stupidity here. It's just okay. No, it should, like, the only things you should need are loaded in this first cell, okay? And then if you didn't change the data structure in the folder, we should just be able to shift enter through that, okay?
Still, I changed the kernel, but I'm still getting no module name.
What?
The Jupyter notebook is in the Cosmo box.
Can you show me what?
What? Sorry. Was I? Oh. Okay. So I was being stupid.
Oh, I see.
So I just need to copy.
You need to the read snap and the G3 read file,
Okay.
and then it should work.
Thank you.
Okay. Yeah. So you okay? Sorry. Yeah, we have to change a few things because you guys will not have 33 snapshots. Okay, that's a good point, but that's okay. Okay, we get that done. No worries. Okay. Okay, let's do it step by step. Has everyone executed the first cell and you guys are at the first cell? Okay, then let's try to execute the second cell. And you should get an image which looks something like that, okay? Because you guys should definitely all have the snapshot 0, 0, 0. It might not be the same redshift then for me because I changed the output list because the snapshots are already a bit big and you guys are 25 or so. So you can do the numbers on that. So the cluster guys will not be happy if we just suddenly spam the disk space. Yeah.
How do you know how many snapshots you have? You said 33 or something?
Yeah, I have 33 because I used one. I changed the output list before you guys submitted the simulation. So that the code works in a way that you can specify some output times. And for you guys, I used a reduced list with 15 snapshots. Like that's even too much because most of the times you will just work with the Redshift 0 output. And we will just see, it doesn't really matter which snapshot at later times we use because after Redshift 1, everything looks the same anyway, okay? So let me explain to you guys what we're actually plotting here in this first plot. It's just a very simple 2D histogram of the dark matter particle positions at the earliest redshift that I put a snapshot out, which is, I think, redshift 6 or so. So what you can see is like there's a lot of, you can actually see the background grid from the initial conditions in this one. that disappears at smaller toward redshift 0. This will disappear, but you see very clearly like where your over densities lie, right? We can actually I want to play a guessing game, so you can. If we execute the next cell, we will do something that Daniel will absolutely hate, because we do the same 2D histogram for the gas density distribution. And that's some high redshift, doesn't really matter. Okay, I think it's 6 in this one. But what you immediately understand is the gas density distribution follows the dark matter density distribution. Okay, so simulation kind of worked, because that's what should happen, because the dark matter carries all of the mass. Okay.
How does Python plot a 2D histogram?
Well, I mean, that's just a column density projection, right?
It's just counted in each pixel.
Yeah, that's counted in each pixel. That's not even
So
weight.
you just get blanks.
Yeah. You will actually see that in a minute, why it's a horrible idea to do that for most of the stuff. But that's okay, because we just want a quick sweep on like, did we do well on that type of simulation? Okay. And let's continue that. So in the next one, that looks for me already like this. This is my redshift 0 output. So what you guys have to change here, change it to the highest snapshot number you have. For some of you, this might be 10. For others, this might be 15. For you, if you have 15, great. If you don't, it doesn't really matter, because it doesn't actually move all that much, okay? That's like a takeaway from this. Yeah.
Sorry, it's just a silly question, but like the file format of these files on the right, on the left.
These?
What are
Yeah, let's ignore them for now.
Okay.
They're like these week. I will explain them, but we come to that. We come to that as we go through. That's the output of the structure finder that we will see.
I think the question is about the 0, 1, 2, 3.
Yeah, like what type of files are they?
Unreadable binary files.
Yeah. Whatever. Yeah, exactly. Volker's favorite binary file. That's why I gave you guys these 2 reading routines, to like cut out the middleman. Like what we mostly use nowadays is HDF5 for all of it, but there's a generation who doesn't like that, so I have been raised by that generation.
I'm of that generation.
You of that generation? Do you use Gadget's binary format? No, you have your own. Yeah.
No, I use my own.
You have your own binary format.
I mean, Jim Stone, I was actually having the same conversation. Like, so Theta plus to use HDF5, but he's just ditched to Theta K because it's a solution to a non-problem for most people. The problem of how to write file to disk is not really a problem. You just write a file to disk and you read back in. And the only problem you have is if you want to read that with another code, you have to write a reader. So HDF5 solves that problem, but when you're doing simulations, it's kind of it's like the last 1%. It's not really like your main concern. And HDF5 is a pretty big library to carry around the place. So people have strong opinions, but it's sort of it's nice to have, but it's sometimes not worth the overhead.
Yeah, I don't care all that much. I think for when you make data set public, HDF5 is kind of nice because I can write a read. Even if I don't have a reading routine, I load in H5Py and I have one in 1 second. So that's a nice thing about HDF5. But if you want to make, I talked to one of Volker's PhD students, two PhD students 2 weeks ago, and what we do in our code, actually all of the cooling tables will be in HDF5 when we load them in. And one of Volker's students changed that back to the Gadget 2 binary, and now Volker is extremely happy that someone is actually not using HDF5 for this, because you should not rely on that library, apparently, which is, I can understand it. Anyway, redshift, lower redshift, dark matter density distribution. Do you guys want to take a guess? What's the most? Yeah, let's take a guess. What's the most massive structure that we will find here? Where is the most massive structure? You want to take a guess? Does that look the same for you guys? Okay, okay. So everything worked out with the random numbers.
The bottom right one.
That one?
Well, no, just up from there, but yeah. Like a node in the bottom right corner.
I don't know actually, so we will see. My guess would be on this one. It's hard to say. It's probably this one actually. Okay, let's do the same for the gas density distribution. You can execute the next cell and you will see why you should actually not do this. You see that in the dark matter already, you see these empty pixels, right? But it's doing fine for most of the parts. So, okay. So that's cool. If that looks.
Yes, so what you're doing is an SPH render with a square kernel.
Yeah, that's right.
With a smoothing length of 1 pixel.
Yeah. It's an approximation. Not saying it's a good one. Okay. So I wanna very briefly talk about the units here because they're weird. So this is co-moving megaparsec. So I already converted back from Gadget's internal units, which comes in kiloparsec. So I just divided 1,000 out when I plotted, right? So that's just up here, pos x, pos y divided by 1,000. And that's why we get megaparsec. You know, co-moving, technically it's co-moving megaparsec, but at redshift 0, it doesn't matter anymore, right? Because there would be a scale factor in that. Anyway, okay. And the h, because all of our simulations are over h, okay? Yeah.
Sorry, so the two things that apply, what's the difference between them and how are you like?
Yeah, so
specifying that?
this is, yeah, sorry, I was a bit quick on this actually, you're right. So when we load in the position array, the way this is structured, you can load it in with a different part type, okay? So 1 will be the dark matter, 0 will be the gas. Yeah, thanks. That's a really good question. I was super quick on that. And the way this format is structured, there's different blocks, and they're actually labeled in there's position, velocities, masses. Then it will write, the next block it will write is the internal energies, the densities, the smoothing length, which we don't load in at this time because we don't need them right now. Of course, the dark matter will not have a density or an internal energy because it's not a gas particle, right? But the gas will have these as well, and that's the part type 0. The way this is done in Gadget and the repo is there's 5 particle types in total. They are historically a little bit, so 0 is gas, 1 is dark matter. Then it becomes weird. 2 is bulge stars, 3 is stellar disk stars, 4 is newly formed stars, and 5 is what we call boundary particles that will be in practice our black holes or sync particles.
So in Gadget, this is the same thing I was discussing this morning. So you don't want to mix particles. You don't have different masses of particles within the same type.
Yeah.
But you have different mass sets of particles.
Yeah.
So those essentially that difference is these sets of particles all have a different mass.
Yeah.
Per cell.
Per cell.
They all
That's
have
right.
the same within the type of star particles. They all have the same mass.
Approximately. they will have approximate. Yeah, depends on the simulation. In that simulation, they have all the same mass. In one of these more complicated feedback simulations that I showed in the morning, we actually will try to keep them as close as to the initial mass as possible, but within a factor of 2, because you cannot guarantee, like, depends on my stellar library how much feedback mass I would get, right? So in feedback simulations, it's always a factor of 2, but that's in principle, right? Okay. Yeah.
So what are the units on the color scales?
Yeah, there's none, because this is just like a particle count.
Particles per pixel.
Particles per pixel. Yeah. It will literally not matter. It would be nice to see the total mass. Yeah, I get it.
Well, given that you can have the particles have a fixed mass and there's a fixed pixel size, so that's effectively a column density because it's mass.
Yeah.
It's grams per centimeter squared.
Yeah, and that it would be, if you weight that histogram by mass on the color bar, what you would get is 10 to the 10 solar masses per page. That would be the number per kiloparsec cubed, right? This is the number you would get. Actually, megaparsec squared. Yeah. Okay, now we actually, and this is typically, you will not, like, this is what we do when we have a production run. We just check whether something went horribly wrong. And there's things that, I had one which was very funny that went horribly wrong, where I changed the number of MPI ranks versus OpenMP threads on the fly. What that did, it actually ended up looking very weird because it only had the MPI parts of the MPI piano Hilbert structure in it. That was a fun one. But yeah, so this looks fine. It has some large scale structure. It's not super high resolution, but we formed some galaxies. And now we can do something with these galaxies. So if we move to the next cell that you can execute here, let me explain what this does. You probably have to change that again back to the highest available snapshot for you. So there's these groups files. So what these are, this is where all the structure. So what we did with this simulation, we also ran the structure finder on the fly, which is a friends of friends algorithm that detects the density peaks and that will essentially find dark matter halos for you and attach the gas in the dark matter halos to this specific halo. When you execute that cell, we will use this G3 read new to get like the FOV structure, and we actually only read in the position and the total mass of each object. That's helpful because if you execute that cell, what you will actually find, we only need to do it for this file because they're sorted by mass. We only want the most massive ones. Okay. What you will find if you print that, you will get a very short list. Okay. So this is the masses of all of the structures that we found. Okay. So what units is that in? What did I tell you guys? How is the glorious gadget unit system for the mass? Per age, what per age?
9 billion, sorry, 10 to the 9.
10 to the 10, 10 to the 10. 10 to the 10 solar masses per age. So if we want to have that guy in solar masses, we have to do something like that. And then this looks like more familiar numbers maybe. So this is maybe the numbers you would, attribute to galaxies and groups and clusters. Because we ran a very small volume, the most massive thing in there is just like a small galaxy group. It has 4 times 10 to the 13. And that's the one we're gonna work with for the next couple of minutes. So you can continue
in this nice little notebook. So now it becomes a little bit. I wrote this up for you this morning so that we don't have to spend too much time on like units and stuff. But what we want to get now is radial profiles of these. So typically the next step after you have made sure that the simulation is not a complete failure, you want to go through some of your halos of interest, which is always the most massive ones, because that's where you have most of the resolution.
I'm sorry, what was your conversion factor?
10 to the 10 over 0.72. 0.72 is the Hubble parameter we used for this cosmology. Actually, no, we didn't. That's wrong. It's 0.67 something, right?
This is the one we specified in the.
Yes, exactly. Sorry, the 10 minutes I had today, I worked on a simulation with 0.72. So I think it's 0.68 or something like that. So it's a bit more massive. Okay, 4.55, no problem. Okay, so something I haven't told you yet is that we running these in primordial chemistry, which means there is 76% of the mass in hydrogen and 24% in helium. This is important because if we want to compute a temperature, we need the mean molecular weight, the Boltzmann constant, and the proton mass. So this small function here, what it will do, I'm not saying it's written super clever, but it's doing the job, is taking the arrays that we just read in above for sorry, did I come? No, yeah, sorry, we read them in below and compute the stuff. I come to that in a second. So it will just compute a mean radius, a mean temperature, a mean entropy, and a mean density. Okay, very stupid, but it works. There's a step missing here if we would have a simulation with unequal masses. All that averaging should be weighted by mass. Well, or volume, that depends now what you want to do. But anyway, you can execute that cell and it will load that in, and then we can compute the properties below with the next cell. And yeah. Is everyone at this cell? And explain to you real quick what we have. So temperature is computed. So this is gamma minus 1. You all know adiabatic index of 5/3. We didn't change any of that. That's the okay. The internal energy is stored in a funny unit because it has actually the same. It's energy per unit mass. It has the same unit as velocity squared. The reason for this is because internally the code thinks of all these things as, well, thinks of this as a kinetic energy, essentially. And this is just the velocity unit squared. You multiply with proton mass, the mean molecular weight, and you divide out the Boltzmann constant, and that will give you your temperature. And if you execute that cell, entropy is a little bit more complicated. There's a fudge factor in here, which is actually, yeah, I should not have done that. That's a bit sloppy. That's the hydrogen number density conversion from internal units of gadget to actual number density. Okay, and because I use that, so I know what that number is by now, so I just wrote it down. But you should not do that. So that should actually have some mean molecular weight in and stuff, right? Sorry about that. And again, there's the, yeah, 0.72 should be 0.68 and stuff. But that's not a big deal for now. Okay, if you execute the cell, you will get the mean radius, temperature, entropy, and density at the position of the most massive halo. Okay, so we center the whole simulation now on the most massive halo. That's what's happening here. So we take the halo position and we subtract from the position the first entry of this, which is the most massive one. Okay, so we center everything on the most massive halo. You got it? Is that cell clear? What's happening in there, roughly? Okay. If you execute that, we will also see, it will also print us which is the most, where the most massive one is. And if we go back to it, somewhere around 17, 18, so it's this one. You guys were right, most of you. And what you get when you plot that, for the density, you get a decreasing density profile, okay? So I haven't put any units here. So you guys get a minute to put the correct units in there. Or you guys can tell me what units should I put there. What do you want me to write down for?
The y-axis.
Yeah, but in what units?
Mass per unit volume.
Yeah, right. So what's the mass unit? Divided by h. Yeah, okay. Let's keep the h. Okay, what's the length unit? Co-moving kiloparsec. So kiloparsec over h. So there's an h. Okay, so what's the mass unit then? 10 to the 10 solar masses over kiloparsec cube times h squared, right? Times h squared divided by h squared, I think. Yeah, so you can put that in. Yeah.
So obviously, like our simulations didn't run as long, and we have I have a much smoother mean density profile. So what is it that in later times is causing those bumps that like?
You mean these ones?
Yeah, because as
yeah, okay. So this is this.
Mine's not.
Yeah. We only got 12 snapshots, not 15.
15 I have the first
starting
one,
to
but
get a
the
little bump?
second one is the fifth one.
What do you guys think are these bumps? Yeah, substructure. Yeah, so this is the substructure around that halo. So what you actually see is that this thing is quite clean of a halo. If you remember the profiles that I showed you from my actual cluster simulation in the morning, they were much bumpier outside. The reason for this is a relatively small galaxy group that has maybe 100 galaxies around it, while the massive cluster that I showed you in the morning has tens of thousands of galaxies around, right? And because this is a reduction to 1D effectively, right? Because we just look at the radial average. Yeah. Yeah. Anyway, okay, I have to speed a bit up.
Sorry,
Yeah.
can I, so how the friends of friends algorithms, how is it computing the overall halo? Like how is it defining the extent?
That's an excellent question. Because I don't know it. I would have to look it up in the code myself. so I work very little on the development of the Friends of Friends / Subfine that has been entirely written by Volker Springel and Klaus Dolak, and everyone is just like hoping for the best.
Yeah, but we are using like the FOF function that we're using.
Oh, that's just like for read-in, right? Yeah. So the way this works, what you put into Subfine, if we think about it as a black box, the particle positions and velocities go in. Actually, only the particle positions go in, and it will spit you out the size of the halo, and the masses go in as well. The size of the halo and its position. But yeah, that would be a whole other school to actually go through halo finding itself. It's like halo finding is a solved problem, sub-halo finding not. So it's very complicated in practice. Okay, I have to speed up a bit. So we're not plotting any units, that's fine. We can talk about that. So if you execute the next cell, you will get a temperature. And I make that short for you, that's in Kelvin, because we already did the unit conversion for that up in the other cell. And you will actually see the same, then you will see in the density, there will be bumps in these, right? And temperature is typically declining for these, like that's a group has a virial temperature of 10 to the 7, so that's fine. So we passed the second test of a good cosmological simulation. And the last thing we're actually going to plot is if you execute the last cell, you will get the entropy profile. And that unit is in kiloelectron volt. Yeah, I never remember myself. To the power of, yeah, three halves or something like that. And that's an SPH thing. So on a grid code, that might look different actually, because this is the issue. You remember why in my cluster simulations, the magnetic field's a bit too high in the radial profile? That's because this thing is plummeting out to like 10, where that would not necessarily happen in a grid code. And what this does for the density profile is this tilting up, okay, here. So in my MHD simulations, that's the reason why I get a too high radial profile in the center. But yeah, I think I'm out of time, right?
Yep, 4 minutes.
Okay, it's okay. We plotted everything we wanted to plot, and you guys can ask me questions in the last 4 minutes. Yeah.
Yeah, I just want to know the last bit that you said that entropy profile is an SPH thing. Why is that? What is that about SPH?
Do you know that?
Well, I don't quite understand the statement that you made, but it's.
Klaus said that a couple of times to me that this would happen in non-radiative simulations all the time in SPH. So I didn't.
I mean, if it was back to the original issue being discussed, it was that in Gadget there's no shock conductivity.
No, there is.
So
yeah.
That was kind of the thing.
So it's true. Maybe there is not in that type of simulation not enough shock conductivity, because what we assumed for this. So it's true. This change. So I use physical conduction. We used the physical conduction solver and switched off all artificial conductivity, which might cause that issue, because in some simulations where I played around with the anisotropic diffusion solver we have, if I increase the flux, the heat flux along the magnetic field lines to a higher value, I actually get rid of that. So it could, for us, just be the parameterization of the conduction we use. That's true, yeah.
But that's sort of not well controlled in the grid code either.
Yeah.
So it's unclear what the right answer is, I think, is the point. Should you have small amount of conduction, or should you have some higher amount of conduction on grid scale?
Yeah, it's the way it's parameterized here is to 5% of the Spitzer value.
If you jack up with a
but-
conduction,
Yeah, that's true. Yeah. Whatever. Yeah,
Sorry, can I ask?
sure.
Yeah, so yesterday you mentioned that for the initial conditions, when we're solving them, we extrapolate the power spectrum.
Right.
Now, like I have 0 for your science.
Actually, well, yeah, kind of.
Yeah. So I was wondering that, because I understand that to do that, you need the cosmic growth factor.
Yeah.
Like at least an analytic or a numerical.
Yeah, you do this in linear theory, actually.
Yeah, so, but I understand that at 8 times, so going up, down.
Sorry, let's back up a minute. What you actually do is you have the temperature fluctuations from the CMB. And you know where they, at which redshift they are. Sorry, I didn't explain it very clear maybe. You know at which redshift the temperature fluctuations are, like 1100, because that's when the universe becomes optically thin to, so the Thomson scattering rate drops, and you actually see that. So that's CMB formation at, 340,000 years after. So there, from that, your power spectrum. That you have to but we don't start these simulations at redshift 1100. So what we actually have to do is we have to extrapolate what they would be at redshift 124, where we start.
Does it have to or want to?
Want to.
You
Yeah.
don't have to. You could start a simulation.
You could, yeah, and it would probably not. You could start at redshift 1100, but
It's just slow.
you waste a lot of computing time on time.
On stuff where you know the answer already.
Yeah, and you can perfectly find. So some people do it in linear theory. Some people do it with like first order perturbation theory, and they produce almost the same structure down at redshift 0. Yeah, but that's more, as Daniel said, that's a choice. We could start at CMB formation all the time. It's expensive, yeah.
Yeah, but the actual shape of the matter power spectrum
Yeah.
at redshift 0, you don't use.
No, we don't use that. No, that's actually what you then get out of the simulation, and you actually find that's quite good fit.
Okay.
Yeah. Sorry, it was a bit long.
So we're going to go to very low redshift now. Negative redshifts, in fact. Which is actually the reason, it's probably a good criteria for using phantom, is if your redshift is 0, then phantom is your right tool. So I deliberately stay away from cosmological simulations because it's a very competitive field with very big codes in it, and I've no desire to compete with that or work in that area. How do I connect my laptop? Oh, maybe it's because I need to plug it in. So I mean, so one of the questions you have is why should I use a particular code? But often it really does come down to what that code has been used for in the past. Is there a plug? We're on the screen. All right. Actually, just before I do that, I'm going to just show you a couple of things from this morning because I didn't have any slides. So just a couple of things. So here is a sound wave with SPH in 1 dimension. But just for demonstration, you can run this for as long as you wish at low amplitude with no dissipation, and you will never ever decay the amplitude. Yep. And just proof of what we did on the board. That's true. Now, what do you think will happen if I run the same thing with 0 dissipation with a large amplitude? Okay, so what happens if I have no dissipation? What do you actually get in a code if you don't dissipate? Well, so the answer is a giant mess, basically. So we're still conserving energy here, but the code tries to do something sensible, which is, so this is what you need shock capturing for, is because codes will try to go discontinuous, but because you've assumed that things are continuous, then you get something like post-shock heating, basically. It tries to increase the entropy the only way it knows, which is to increase the actual kinetic energy of the particles, because it can't convert that into heat. So the point of shock capturing is actually just to take that small scale motion and convert it into heat. That's what shock capturing schemes actually do. So if you then take, well, some appropriate scheme, Riemann solver, approximate Riemann solver, whatever you want, artificial viscosity is an approximate Riemann solver, then you get nice, well-behaved steepening of your wave. Okay, so this is the situation, same again. So this is an entirely discontinuous jump to start with. So we're going to run one of these in just a second. But there's two important things here. So there's two kinds of discontinuity. So there's a shock. Well, this is a rarefaction, but basically there's a sound wave that travels in each direction. So at least in hydro, you get one wave in each direction. So there's a sound wave traveling backwards from the initial jump and a sound wave traveling forwards from the initial jump. So that's the initial jump. I just imposed, it's called a shock tube because they literally used to do it in a tube. You'd have like a little membrane in between the middle, and they still do, I guess, in some labs. You have a little membrane in the middle, high temperature, high density gas on one side. I think they shoot it out with a gun, and then the gas just goes whoop into the other side. And so it became like a kind of very standard test problem for codes because there were lab results in the first place, but there's also analytic solutions, so which is the red line. So I mean, if you say, you hear these stupid things occasionally, so like, oh, you can't do shocks in SPH or something. I mean, how many would you like? But there it is. And what we talk about, shock capturing, is really just making sure that you don't get these post-shock oscillations. That's the kind of key goal. And so then there's a sort of argument about how thin you can get a shock, because obviously it should be, perfectly thin according to nature, or not perfectly thin. There is a shock length, but that's due to the true dissipation scale, which is the scale in which molecules actually collide, which is tiny.
How many targets did you use for this one?
Can't remember. Not very many. This is 1D.
Yeah.
Don't know.
They saw that in the grid code, and I think it looks better in the grid code.
It's of order a few hundred, to a couple hundred maybe. You can count them up. I don't know.
Yeah, Lamar had 100 on one day.
But there's another bit which is the source of much confusion over the years. So this discussion about conductivity is one of them. There's another kind of discontinuity here as well, and that's called the contact discontinuity. So it's where the two fluids were initially in contact. And you have to be careful about this one as well, because it's not a shock. So the pressure is continuous. Where's the pressure? Here. Pressure is continuous across the shock, but density and temperature jump. So a contact discontinuity is not a propagating wave. It's just a place where the pressure should be uniform across it, and the density and temperature jump. Yeah. Now, but you do have to treat that in a code. So you have to make sure that, again, that discontinuous thing doesn't give you little blips around the discontinuity. And so there's special schemes for that. So in the grid-based community, so for example, the HLL scheme deals with shocks, but it will tend to massively over smooth your contact discontinuities. So the HLLC scheme kind of accounts for the contact discontinuity and actually does a much better job of not dissipating it. Sort of irrelevant, but one of the consequences of the Hamiltonian is that particles do feel each other, and so they don't do random things. They do have a minimum energy state that is well defined. So the particles have a kind of grid. It's the fact that they want to form these locally isotropic arrangements, and that is why SPH works. It doesn't completely turn into a Monte Carlo method, which it would otherwise. Even if you take what seems like a pretty ordered arrangement, there is still a preferred arrangement of particles, which will be found eventually if you wait long enough. There it is. Yeah. Okay, but so the one little extra piece here. So that's what happens if you run a shock tube with zero dissipation. So same thing before. You get this kind of heat that we need to convert into actual increase in entropy. So if you solve that with just viscous dissipation, so that could be called artificial viscosity, but it's the shock capturing on the shock. But you still get left with this kind of blip, and this traditionally is called wall heating. So it's a very old, well-known problem that if you get a contact discontinuity that's very sharp, you get this wall heating problem. And you can see why. It's because the density is like perfectly smooth here, but the U is discontinuous. And so therefore, the pressure kind of has this little blip in it as well. Okay, so the reason that can be bad is that, okay, so you treat that with what we were talking about before, is shock conductivity, which is kind of implied in these other schemes as well. So they have fancy names, but in the end, what you're doing is you're applying some viscous dissipation to the shock and some thermal conduction to the contact discontinuity. And that's what shock capturing basically is in simpler language. But it can be problematic. So this is like the problem that was argued about for 20 years, is like, I was still argued about. I mean, I don't know, I'm still angry. But it's a really dumb problem, right? Just a Kelvin-Helmholtz instability. You move the fluid one way in that direction, you pull it back in the other direction. But the key thing is there's a density jump here and there's a temperature jump. So if you do this with no density and temperature jump, there's like nothing to see here. But if, you know, what the important thing is, this is a 2D contact discontinuity. Yep, so if you do something dumb, like don't do any, well, so this is what it should look like, I guess. Just some nice rolly instability, as in the situations that are genuinely unstable. But if you don't do anything clever, you can pretty quickly end up with like this. This is not me doing a good job, this is me deliberately doing it badly. Is like you get something that looks a bit more like sort of snot, or some kind of, what it is basically that blip that you saw in 1D kind of stops stuff properly mixing across the discontinuity, but it's got nothing to do with the fact there's an instability here. It's the fact that we're not doing shock capturing properly. Yep, so you have to be careful with your shock capturing because this is a discontinuous interface, and you have to be careful that you equalize the pressure across it correctly. Okay, so that's, well, so then you get the normal version, right? So it's got nothing, the reason a repo was written was that this is like a problem. But it's not a problem, it's just, you got to be careful with the shock capturing, that's all. Yeah, everyone happy? Jess.
I think on the very first and second slide, the only difference was the amplitude. I don't know if the shock was formed in both cases, but in the one hand, it.
This one?
Yeah, so that's 10⁻⁴, and then you showed the next one is 0.1.
Yep.
Why was that? Is that the only difference?
Yep. Just the time to shock. Well, so actually there's a mathematical problem with the fluid equations, which is why is $1 million if you can solve the Navier-Stokes problem, is because this formation of a shock inevitably happens in the fluid equations, because if you run that for long enough, it will steepen. So the real way to think about this is what's the absolute velocity here? So in the case where you have no pressure, the two fronts are just going to catch up with each other like that, because they just follow dV dt as naught. And so just how long that takes. And so with 10⁻⁴, that's going to take t equals 10 to the 4. And so with 0.1, that's just going to take like of order.
Oh, I thought the first slide would run forever and never change.
No, definitely not. But I could arbitrarily lower the amplitude to make it happen at a later time, but it will always form a shock eventually. So in mathematician language, that's the problem, right? So even if you take 10⁻⁴, you could in principle run it for t equals 10 to the 100, and it would still form a shock. So there's a kind of what they call a late time blow up in the Euler equations, which is why you win $1 million if you prove that. I mean, we don't care because we know how it works, but there is a mathematical, I think it's a non-problem, to be honest. But I don't know, win $1 million for yourselves. All right, enough of that. All right, so we're on the practical stuff now. So there is a GitHub, which I believe you got emailed. Really, this is just a front page. It's, can you see this? GitHub Daniel J. Price, CCA_school. Is everyone there? Yep. Okay, so first of all, there's some fluids notes. We're going to go through a little bit of some Friday next week on MHD. But what you didn't get a lot of is actual fluid dynamics. So this has got nothing to do with numerics, but this is from a course I give at Monash. There's some lectures which you can watch, but we're just going through basically why do we think about sound waves and shocks and things and the basic understanding of that. And there's a bit of MHD and there's some dust gas as well. So again, none of this is numerics. This is just pure like background reading basically of when we're talking about doing hydrodynamics, what sort of things should we be talking about? So these are just for free. You can have a look. It's sort of very, I mean, I do both things, but it's written from definitely my perspective, which is like using Lagrangian derivatives all over the place. So for example, often the first thing you see is derivation of these things. We don't derive them, we just write them down. But you know, fluid equations in the form that then Lagrangian straight away. Yeah, blah, blah, blah. Yeah, so have a look anyway. But some of these things, especially, I guess, like equations of state and things. So you hear about isothermal and adiabatic and this kind of thing. You should read some of this before you use the fluids code. Okay, so on the practical stuff for Phantom, so I've written a little documentation page, which is in the official Phantom documentation, which is here. Two more things I'll add. So that's the notes I just showed you. But the notes from this morning are actually very closely followed. So this was actually a summer school I gave a long time ago. And I just wrote it up as an actual paper. But you will recognize, oh, that's the archive version, but okay. But you will recognize the kind of structure we went through. How do you calculate a density? What's the density estimator? How do we go through, so some of the kernels. So if you want details of what we covered very briefly this morning, it's all in this one. In particular, like if you want to start with the Lagrangian, derive your equations and arrive at your equations of motion. So that's done in a bit more detail than we went through. But that's like the printed notes version of this morning. This probably the MHD is a little bit obsolete in there now, is the main thing, but the other stuff is the hydro hasn't really changed. Okay, let's go back to where we were. So that's that one. There's also a couple of videos that you might like if you're doing anything SPH. There's also a Joe Monahan introduction to SPH video. Joe Monahan was one of the inventors of SPH, so he was my mentor in some way. So he was my master supervisor, I guess, back in the day, which is why it became in part of my bones. But if you want to see what he looks like, it's in the video. All right, so here we are. So if you can just jump straight into this page, we can get you set up with Phantom. So I assume everyone knows how to log into Rusty by now. Yeah. So if you're in Rusty, we just need to module load the Intel compilers. So let's do this live. I think I'm still logged in. Is everyone on that page? So that page being this one. Well, so if you go to, we're basically just in the Phantom documentation, but I just made a page. Let's just go to the very beginning of this thing. So that's the Phantom documentation. I'm in getting started, and then I'm in quick start. And quick start, I have a getting started on Rusty.
Where was the link for this page?
Yep, so that was linked from the original repository here. So that's the getting started on Flatiron.
Do you need to SSH minus Y?
Yes, you do. So SSH minus Y is the same as SSH minus X. Enables you to forward X Windows connections over the network. Actually, so for this, please don't log in through your Jupyter thing. So if you can just log in through a regular terminal, that will be more helpful. Mainly because Jupyter doesn't allow you to pop up Windows, as far as I could tell, unless there's a magic thing I miss. Okay, so we're typing module avail to see what's available. So just to show you how we got to this. So I know that I need the Intel Fortran compilers. So Intel Fortran compilers have a name like Intel 1 API compilers on this machine. So all I really need to do is module load that. It's going to tell me I already have them, probably. Can you see what I'm doing? But I find this really annoying having to remember what modules I want to load every time. So just a quick hack. So what I tend to do is I make a file called .modules. In fact, I'm going to just make it now in my home space. And I just edit this file and stick in my module load commands into that file. .modules is nothing special. It's just a file name that I've decided to call something in my home directory. It's just a nice little trick. And then you just want to go into your bash RC file. And we're going to put a few things in here, which you should also copy from the page. So we need to paste a whole bunch of things in here. But the first thing I've done is source twiddle/.modules. Actually, let's type it all directly. Let's pretend I've got nothing in here. Okay, so I'm going to go to this web page where we were. Okay, so first of all, I want to make this source twiddle/.modules. So I can change the modules files without having to put them in my bash RC. This is in my .bash RC in my home space. So I won't have another terminal open on Rusty. Maybe I do. Yes, I do. No, I don't. Okay, so just to clarify then, so I'm in my home space, CD, nothing else. And I've just, well, I made a file called .modules where I put that module load command, just so when I log in next time, it's going to happen. Yeah, and if you want to find the name of that module, I did that by typing module avail to find what the name of the Fortran Intel compilers is. Yeah, that's how I found the name. And then I put the name in my .modules file. Okay, and then I've edited my bash RC. First of all, so source twiddle/.modules just runs the commands in the .modules file first. Okay, but then there's a couple other things we're just going to get it set up with here. Let's just skip that one for a minute. So let's just go straight to this edit your bash RC file. And you can see just some lines to cut and paste here. Just cut and paste those. Okay, so what are these things? So system equals Rusty is something for the Phantom makefile. So I've made a little block that configures the compiler appropriate for Rusty. Ulimit minus S unlimited sets your stack size to be a bit bigger than the regular one. So that's important because we have, for example, the neighbor arrays in Phantom are individual to each thread, and so you need a bigger stack size. The OpenMP stack size is the same reason, and the OpenMP schedule, so there's a bunch of loops in Phantom which are scheduled at runtime, so you can choose to play with the schedule if you want, but dynamic is probably the best default, and different compilers will give you different defaults otherwise. Okay, so this is just how you want the parallelization to be scheduled, which you, so wow, should I explain that? So you parallelize a loop, the most dumb thing you can do is each thread takes like a chunk of the loop, so that's called static scheduling. Guided scheduling is everyone take a big chunk first and then take a little chunk and then take a little chunk, then take a little chunk. Dynamic is just trying to figure out the best way to load balance, which is a bit more expensive, but it makes sure that everyone's got even work, basically. But again, you sometimes want to play around with it, which is why we leave it as a runtime variable. Okay, let's just skip down to the bottom of this as well. So I'm just going to get you to paste these 3 lines as well while we're here. Because we had a little problem with the module version of Splash on Rusty, so I just installed it on my home space. So if you can just copy these lines exactly as written, you'll get my version of Splash as well. So that's just, okay, so what are we doing here? I'll just explain this one again. Well, that's just a variable, but I'm putting my, so my Splash is compiled in my home space in a directory called Splash /bin. So I'm just putting that into the path. So the path is where you look for programs. And this LD library path is the path where you look for libraries. So there's a library it needs to find at runtime, and I'm putting that into the LD library path. So this is, we should do a module load, but there's just a technical issue where it's seg faults for some reason, which we want to avoid with you. So if you just borrow these 3 lines, has everyone got that?
But our Splash directory is the same as yours, no?
Say, yeah, use mine if you can. So you can install Splash in your home space if you really want to, and that would also be fine. So if you just wanted to install, so if you're like working on a new machine and you just want to get your own copy of Splash and it hasn't been installed by the system admin, those 4 lines will do it for you, and you can use your own. And then you would just change this to your home space instead of mine. So if you want to do that, go ahead. That will also work.
Sorry, what's Splash?
We'll see in a minute.
Okay.
Yep. I'm just preempting everything we're going to type into this bash RC file. Yeah.
When I edit my bash RC, it says permission denied.
You cannot have you're editing your bash RC, not someone else's. So if you type CD, that will get you to your home space.
Yeah.
And then edit your bash RC. You should absolutely have permissions to edit that one.
Oh.
Okay, so just to clarify as well, so the bash RC file is just a file. So for example, if I put echo, I do this with students. If we just do echo, like hello Daniel, at the top of this file, then if I log out of Rusty, I'm not going to log out of the gateway, but if I log out of Rusty and log back in, you don't have to do this, but you'll see that when I log in, it says hello Daniel. Yep, so the point of the bash RC file is it's just a file that gets executed every time you open a terminal. Everyone clear with that? Has everyone got the stuff required in your bash RC file? Just hands up if you're stuck or if you need help. Actually, can I head up to you, Ulrich, to check on people as well? Well, and so you can, if you're not stuck, then you can keep going. Okay, if you're not stuck, we can go back to here. Actually, Ulrich, do you want to try and debug does this guy put back? Yeah. Has anyone else got issues? No, I think we're okay. Okay, so we're set up. Now I'm going to just do this from scratch. So pretend I've got nothing. Okay, so then we just want to get a copy of Phantom. So we can do git clone. So it's github.com, Daniel J. Price. Well, I'm Daniel J. Price. There's too many Daniel Prices in the world, unfortunately, including at least 2 astronomers. So Phantom, yeah.
I think you might want to clear sometimes so that.
Oh yeah, good idea. That's a good suggestion. Clear. Let's try this. All right. So we're in the home directory now. Git clone, https github.com, Daniel J. Price, Phantom. And you don't need to add anything else. That will make a directory called Phantom by default. Okay. Success? Failure?
I have a question. Is there any difference between G-Fortran and the Intel compilers?
So Intel, like typically we get about 20% faster speed out of Intel with OpenMP. So that's the basic reason. But in terms of will it compile the code, both are fine. I mean, G4tran's got a lot better over the years. It's the free one, obviously. So you expect when you pay money for a compiler to get something better out of it. So what you get is about 20% in speed, but your mileage may vary. There's nothing wrong with G4tran. And Phantom, so for example, so why do we check out straight from the repository? Why didn't you download like the stable version or something like that? The answer is every version is stable. And what I mean by that is we have a very comprehensive test suite. Sorry, go back to the repository. In fact, I changed 2 things like the other day, and it took me 2 days to get it to actually go in, because every time you do a pull request, there is a huge number of things that get run. Let me find the latest one. Also, they're called actions. So, for example, this is just a little thing I did. So we check, for example, these are not even the full ones. So, for example, build test. What's the build one? Well, I broke a bunch of them the other day. Actually, we break them all the time now, but nothing broken can go in the master repository. But it really tests so many things that it's really hard to get it to pass. But I mean, just for example, oh, sorry, that's what I was missing. It's on the left there. Yeah, so look at the build test, for example. You will see that it checks, for example, I compile with system equals G4tran. I compile every possible combination of Phantom. I compile with system equals ifort. We run a very comprehensive test suite with debug equals yes, debug equals no. I make sure the code has no warnings in it with G4tran, otherwise it fails, can't go in. I even run every possible setup of Phantom, make sure it works, and doesn't segfault and doesn't do things. So basically anything that goes into master is pretty much stable. So you should kind of ignore the releases down the side here. I mean, I do that once a year just to make you feel bad if you're using an old version. But really, like anything that's in master should be regarded as latest stable version. So it's sort of continuously released. Okay. Yep. So CD Phantom. Now, the next thing is really just good practice. It's not compulsory. It is compulsory because it's good practice, is tell me who you are. Okay, so let's do this. Yeah, because what I don't want is random rubbish in my commit logs. Yep, so when you tell me your name and your email address. This is because when you start making changes to the code, I want them back, and I want them back with your name attached. Yep. So this is a global thing, so you don't have to do it once on Rusty, anywhere. That's why the ---- global flag exists, and Git will know for all time who you are. But otherwise, you just get junk in the commit logs, which I don't want. So do that. No, so for example, how do we contribute to a code? We haven't really talked about that. The answer is just make changes in your local code directory. So for example, let's just delete it all. Let's just delete, I don't know, force.f90. Okay, good local change. Okay, but git status will tell me, okay, the difference between mine and the repository version is that I've deleted a file. So first of all, this is good. If you've made a change and you want to just revert, you just do git restore source main force.f90, and it will get me back to the undeleted version. But for example, if you made some changes, so the next thing to do would be git rm, okay? And then I want to like really do that change. So I would then commit that change, delete force. Okay, deleted, no worries. Okay, so it seems like my code's up to date. That's good. I could push, and that would just push where? So you're not allowed to push to my repository. So what you do is you make your own fork of Phantom. You click a big fork button. You'd basically do git remote add your fork, which you have to do it in SSH if you want to push rather than just read. So if you git at github.com, Ulrich Steinwandel.
Oh, that's pretty good.
Yeah. Phantom. So that's kind of the thing you get. I think it's with a colon. So for example, you just put your fork there, and then you, I think you have to give it a name like Ulrich. Yep. And then if I just git push Ulrich, okay, the repository doesn't exist, but in principle that would push back to somewhere else, and then you could issue a pull request into the main Phantom repository to contribute a change. So this is what I want you to do. You'll go off and do maybe some small things, but eventually you have some little local changes that you would like to put back. You don't just push them back to my repository, you push it back to your fork, and then you issue a pull request. And it goes through all the checks. So even I'm not allowed to push to my own repository. I have to push to a branch, and then I issue a pull request from a branch onto my master, goes through all the checks, goes into master. Yeah?
What would happen if you tried? I feel like I'm always afraid I'm accidentally.
So I know that I will have permission to push, because you can't even deny yourself admin permission, but you can block the master. So I block the master thread from anything, and it does warn you, doesn't warn you. The command line tells you shouldn't have done that. You overwrite the thing, but for example, it won't let you won't let anyone else just push. It also means it's also really simple just for permissions. So you guys obviously don't have permission to edit Phantom on the repository, but you have permission to fork it, and then you have total permissions on your fork to do what you like. And then the merging of those two things is called pull request. And so that's just a really good way of separating out those permissions as well. You don't have to get an account to contribute to Phantom. You just get a GitHub, you clone it, you do stuff, you push things back. Okay, that was a short Git lesson. Okay, but so that's why it's important to tell me who you are. Now, what have I done wrong here? Well, let me just, because it's a Git copy, and I'm just going to delete it and get a new one. And just git clone again. Okay, so we're here, we've done this, we've done this, we've done this. Now we just want to actually run a calculation. Okay, so far there's nothing complicated. Number one rule is don't do the calculation in the code directory. And so this is usually explicit on a cluster like this. You know this already. Basically, you should run things usually on a supercomputer, you'd have a home space and a scratch space. And so you should run stuff in the scratch space. So they've already done this for you, actually. You can see that Ceph here is just a soft link. Sorry. Ceph, let me just clear. So this Ceph thing is actually just a link, a soft link to mount Ceph users dprice. I prefer to always call mine runs on whatever machine I'm on, so I can cd runs / whatever. So that's what I'm saying here is make a soft link called runs, then I can cd runs. But there's already a soft link called Ceph here anyway, so whatever works for you. What's a soft link? A soft link is just ln-s, the place you want a soft link to. In this case, I just want to, well, let's do it properly. So mount Ceph users dprice. That would be called, so you can give ln-s with one argument. I would just call it dprice locally. But I want to call it runs. It'll tell me that the file exists. Oh no, that worked actually. Yeah, so you can see now I've got, well, it's the same thing. I've got a soft link called runs so if I do cd runs and I find out where I am, yeah, now I'm really in that directory, but it appears like it's a directory off my home directory. Just so when you type cd, then you just do cd runs and there you are. Or cd twiddle / runs will get you there. That's,
what does L stand for?
No idea. Link maybe? It's ln-s is a soft link, which is like a shortcut in Windows language. Or okay.
Do software play nicely with input files or something if you have some directory that you put in?
Yeah, they behave like regular directories. Okay, so the next thing in the runs directory, we want to make a directory. I'm just going to delete the one I had previously. Sorry, make dir. Let me clear again. Let's run a shock tube. Okay, so it's a blank directory at the moment. So how do we start a phantom simulation? There's a magic script. So I can try tittles. So I go into the phantom code directory. I find the script called write-make.sh. And you notice I found that script by tabbing. So I did twiddle/ph. I pressed tab, and then I pressed tab with an S with a script. Yep. And I pressed WR, and I pressed tab again. Yep. Okay, so it takes one argument. The argument is the compile time configuration of Phantom that you want. So in this case, this is called shock. How do I find out what I want? The answer is down here when we get to more interesting things. So this is the name of a parameter of which it can adopt many variables, and there's a whole table here. These are the good ones. These are all the ones that anyone's ever had. Okay, but basically it's a block in the makefile, which I'll show you in a second. In fact, I'll show you now. But let's just do the command first. And we're going to create a local makefile. So the greater than means put the output of that command into a file called. So if I don't do the greater than, it will just show me that on the screen. Yeah, which is just a giant mess. Yeah, but I want to put the output into a makefile. Okay, so you should have successfully done that, and the output of that should be a makefile in the current directory. Okay, so what does this makefile have that's special? All it has at the top of it is I've hardwired this variable called setup, which is just a variable in my makefile, and it equals shock. Yeah, so when I'm in this directory and I type make, it's going to compile Phantom with setup equals shock. Yeah. There's some other things there as well, but don't worry about them. Everyone happy? Okay, what's the next thing I would type if I've got a directory with a makefile in it? What does it want from me? Make, indeed. And we also want to make two things. So make will just give you the basic Phantom binary, but we also have an initial conditions generator called Phantom setup, and we want to make the initial conditions generator as well. Okay, so how does it know to use the Intel compiler? That's because in our bash RC file, we put system equals rusty. In my make file, I have a little block that has if system equals rusty, this is the compiler you want to use. But so system equals ifort, for example, you could use as a sort of generic one, or system equals gfortran. There's one little extra thing which we will go through, which is configuring the submission script, which is also done in system equals rusty. But everyone should be compiling now. Is that true? Yep. Yep.
Make sure you source your bash RC.
Oh yeah, so if you didn't log out and log in like I did, you have to source your bash RC to get those variables working. What do I mean by source your bash RC file? I mean type source space twiddle/.bashrc. Or you can log out of Rusty and log back in again. That's the same effect. So if you want to run a tidal disruption event in general relativity instead of a shock tube, what do you do different? You say GRTD instead of shock, and that's it.
Not how it works.
Sorry.
Not how it works.
Well, so one of the things with Phantom is we are a bit more general, right? Because stars and planets doesn't mean one thing. It means a lot more like different simulation types than just running the universe. So we do try to be a bit more, bit easier to change your problem, which is, I guess, why these configuration blocks exist. So basically, they're mostly about what you want to set up. So there's a different collection of compile time options, which is listed here. So what you want switched on, like basically the basic blocks of physics. Do you want MHD? Do you want self-gravity? So self-gravity means the gas feeling its own gravity. Yep.
I have problems compiling. Yeah. Yes. I have this double slash, which shouldn't do that. And
So that's your, like, in your bash RC, you need system equals rusty, or you need to source. So I just didn't really cover this. So if you weren't sure about the variables, source.bash RC. Yeah. And if you want to just check what's set, I mean, env tells you like all environment variables set on your system. Okay. But somewhere in there, in that giant list of mess, what a mess. But somewhere in there, we have got system equals, where you can just do echo. So echo $system should be rusty. So it's just an environment variable I use in the make file. Okay, let me just show you. Actually, let's go through something before we run out of time. Okay, so we just run our Phantom setup. It asks you for one thing, which is just the name of your simulation. Call it whatever you like. Shock. Okay. Okay, so I don't particularly like the questions. If you don't like the questions either, just ignore them and press enter. It says, what kind of shock tube would you like? Would you like a side shock? Let's just say yes. How much resolution would you like? 256 particles in the left side, please. But it's going to be, so Phantom is entirely a 3D code. There's no such thing as a 1D problem in Phantom. But we're going to run a 1D problem in a thin box. So 3D box that's thin. Okay, but if you run Phantom setup again, so what that did is it generated this file called shock.setup, which is a parameter file for the initial conditions. And every setup's going to have different parameter file. So it's giving you some defaults, which are probably, we're just going to go with the defaults here. But you can see it's like density on the left, density on the right. So it's sort of sensible setup for a shock problem. Just the parameters you would typically want in that problem. Number of particles in terms of resolution, what gamma do you want, how long do you want to run the simulation for? Yeah. Okay, so that's then now the input to Phantom setup. So I'm going to run Phantom setup again, and it won't ask me any questions. It will just use the parameters in the file now. Yeah. And actually go through with the setup. So the questions are only in order to write that .setup file. But after that, you can change what you like in the parameter file. So a lot of the setups don't have any questions at all. Some people like questions, some people don't. The one thing that's tested every time you do a pull request is if you press enter, it's guaranteed to work. Okay, so what that produces is two things. So you've got a .in file, shock.in, which is the parameter file for the main code. And you've got this dump file, we call it. It's a snapshot, but it's a .temp snapshot. And that basically means we haven't gone through the density summation. So it's a snapshot with positions, velocities, I guess for the smoothing length and a particle mass, but it hasn't actually been through the procedure of iterating density and smoothing length, so it doesn't have a real density in it. Okay, so the first thing the code will do, so it tells you what to do right here. It says run phantom shock.in. Now, of course, I shouldn't do that on the head node. Okay, so I could just run on the head node. Let's do that just for a second. 56 cores on the head node. I think it only gives you one anyway, which is going to be very slow. Because as far as I could tell when I was trying to run the head node before, it was just, if I topped it, it just said 1. Let's not do that.
Sorry, I missed the part where you generated shock.in.
Okay, so I just ran phantom setup shock. Yeah. I ran that twice, once to get the .setup file and once to use the .setup file. Okay, there's a bunch of output you can print. One of the things it does print is code units. Now you can see we're running a shock tube, so all the units are just set to 1, which is going to give you some meaningless garbage if you try to visualize that. I mean, 1 gram, 1 centimeter, 1 second is not the real, I mean, it doesn't have any units, a shock tube, it's just a dimensionless problem. So you can apply whatever units you like afterwards. But you should realize that these units are kind of arbitrary. They're applied after the fact. They're not really used in the simulation unless you, for example, have some physics that uses like real temperature. Or if you're using real temperature, then you have to care about what the real units are. But Phantom's all in dimensionless units, like most codes are. And so these units are only used depending on what physics you employ. So if you employ physics that cares about the real temperature, which the fluid equations don't, and MHD doesn't. But for example, if you have molecular line cooling, like atomic line cooling, that cares what the actual temperature is, and that's when the units are important. But apart from that, they're just a kind of post-processing. Okay, so what we want to do is run it via the queue. So you could just put all this stuff in the queue, but there's a little make queue script. Yep.
Do you have to worry about the CFM number in this image?
Yes, we do.
Are they in the?
Yes, it is. I'll come to that in just a second. Okay, so just make QScript. It wants one argument, which is what's the name of the input file. So I want imp file equals shock.in. And what it's going to do is generate you a SLAM script like that. Actually, we're only allowed to have 10 CPUs as well. So just set NOMP equals 10. This is all in the documentation as well. And all it does is change that number from 64 to 10. And we're going to put the output into a script. You can call it whatever you like. I call mine run.q, but whatever you want. Okay, and run.q is my run script. And it just sets a bunch of things. I mean, actually, there's nothing in here apart from the basic SLAM commands. There's a time limit, which is customized. So like system equals rusty, I've left that as a week. Just sets OMP num threads equal to the number you've asked for. Schedule equals dynamic, like we had in the file. And this little command down the bottom is just something useful for if you restart the code, it doesn't just put the output into the same file. It updates the number in the log to like, so the first time you run it, it's 01. If you do a restart, it's 02, 03 in the output of that would normally go to the screen. Okay, so Phantom shock.in. Oh, sorry. So now we can just choose SPH.
Well, we need to change the partition for temp.
Yes, so just do SPH minus ptemp, run.q, and go. Yep.
Is the job name randomly generated?
Yes, it is.
Yeah.
That's my wonderful 3-line. It's my favorite 3-line script ever. Random word.perl. There it is. It's 3 lines. So if you, yeah, there it is. What is it? Oh, okay, so I've got a backup. There's a backup plan, but the basic script is 3 lines because sometimes like user dict shared words doesn't exist. And in that case, I choose a random Australian animal. Otherwise you just get a random word from the dictionary. But yeah, I was pretty proud of that. It's 3 lines. Random number is int rand $hash word list. Yeah. Do you know what a qual or a quokka is?
I know quokka, yeah.
Yeah, you should know what a quokka is. Yeah, qual is like pretty fierce animal that just eats like meat. Dingo eats babies. Actually, everything, most of these things will kill you. Croc, shark, fruit bat probably will also kill you. Okay, so you can do SQ minus U $user. $user is like your username, so that will work for everybody. You can see I'm still running my cosmological simulation from yesterday, apparently. Oh no, actually I ran something before. But okay, so my job is running. You can see my job is running because I'm already getting outputs. So I'm getting a series of snapshots, shock, blah, blah, blah. And I also get this shock01.log. So shock01.log is what would have gone to the screen had I just run it locally. So shock01.log gives you the main log from the code. So first of all, it repeats the input file back to you, so you remember what you ran with. But then you've got a series of basically time steps. There's a little code timing table, tells you how long it's spending in different routines. So normal output of this is 100% of time spent in the step routine, which consists of basically calculating density, calculating force, and building a tree. So normal output of an SPH calculation is not much time building the tree, half the time doing density, half the time calculating the force, which are those two summations we described this morning. There's a summation to get the density, there's a summation to get the pressure gradient.
What's the one it's telling, is this for the time step with the?
This is just, this one.
When it's saying kilometer.
Yes, so this is what's controlling the time step. So there's a Courant condition. DC print is I just want to hit the time of printing exactly. So it takes a short step just to hit the time of printing. Toll V is not important. There's a small, it's described in the input file, but most of the time it's just controlled by the Courant condition. There's another condition called the force condition, which we take h divided by the square root of the acceleration, which gives you a time step control. It's not usually the dominant thing. If that's the dominant thing, it's usually a sign that your simulation's got weird stuff happening in it. So you should, Courant condition is the normal thing to be controlled by. Okay, so this simulation's finished. So Splash is the tool we use to look at these things. So as Ulrich said, you don't really want to look in the binary file yourself. So Splash is really best at sort of interactive visualization. Its job is to do the thing we talked about this morning, which is to give you SPH interpolation of things and show you the smooth field. At the time when I wrote Splash, this didn't exist there was no tool for this. It's kind of just a plotting tool as well. Obviously, everyone wants to use Python to do plots these days. Splash does do plotting, but so there's a new, if you want to do things in Python, there's a really nice package called Saracen, which basically does the things that Splash does. And it's linked from the Phantom documentation in Python, but Splash is my baby, so here we are. So you're going to get text menu, which is the thing that confuses people the most. So for example, I want to plot density against X. So it's just column numbers, basically. I want density against X. You can press enter for other things, and you should get a plot that shows me plot of my particles. Yep, and I just press space to go forwards in time. Nice movie. Yep. What I really like is the exact solution here. We're doing a problem with analytic solution. So how do I get that? Press Q from the window, press O for the options menu, I press 8 for the exact solution. It's pretty clunky, but it does work. 3 for a shock tube. Shock tube reads the parameters straight from the .setup file. So it knows which exact solution to plot. I'm going to do one more thing, which is change the exact solution so it's red, line color to 2. Too many options. Ignore them all. Yeah. Don't let me tell you, SPH can't give you a shock. Yeah. Okay. So this is a 3D shock tube. There's no cheating here. It's 3D shock tube running 3D. So it's not like a 1D version of the code or anything. It's just the actual 3D code running.
How many particles do you use?
Don't know. Well, so it tells you when it reads it. So there are 161,568. But it's sort of a random number because you don't really choose the number of particles. So what's actually happening here? You can plot. Has everyone got some output? Yep. Are you looking at it? Yeah, so if you're very confused by Splash, you can use the command line only and not look at the menu. So if I want density, so to minus y density minus xx, that will just make that plot for me with no questions asked. Now, obviously, I lost my exact solution, so let's go put it back. So 0, 8, 3, no. Now, what I should do is save. So saves it just saves a couple of files. It's basically the parameter file for Splash, which is splash.defaults, and the plot limits, splash.limits. So those are files that you could, in principle, go and just mess with if you wanted to, if you're a pro user. They're like nameless, like Raman was talking about. So you could, in principle, edit that file. In practice, we don't really, because everyone loves the text menu. And then there's just like column limits, so min and max for each column in that. Okay, so if we do that, now I've got my exact solution. I wanted it red, so 09, 1000 exact solution points. Red, please. Ignore the rest of the options. Okay. What if I want to plot other quantities? Well, so I set multiplot. Yeah. So on 2 plots, yes, on the same. Oh, no, I don't. Let's go again. 4 plots per time step, not the same y-axis. Yes, for the same x-axis. I want density, velocity, thermal energy. How do I get pressure? We could go smoothing length for the moment. Let's go with alpha, actually. Why not? How do I get pressure? So I can get pressure because I can calculate extra quantities here. So calculate extra quantities. And I'm just going to get a few things by default. So pressure is just one of the pre-calculated things. There's pressure. Okay, and hopefully multiplot should work. Yeah, there it goes. So the main reason that alpha is interesting is it shows you the shock detector in action. So it shows you that alpha is going, basically responding to become 1 at the shock, and it's like 0 away from the shock. So that's like a sort of shock capturing switch, which is saying I want to apply dissipation here and not here.
This is going back a little bit, but were you saying that you don't necessarily set out choosing the main particle equivalent, but that is calculated based on?
Well, so you have to, obviously, if you have a density jump, you have different numbers. Let me show you what the actual particles look like. So I'm going to just undo my multiplotting by going back to 1 plot per page. So let's look at what's actually going on in the simulations. This is actually like a bunch of particles set up on the left and a bunch of particles on the right. And what they actually do is like move like that and do the whole shock thing. Yep, so it's all looks like a normal code, but it's not. Well, it's normal if you're doing particle methods. And if you wanted to plot the smooth version of that, how would I do that? So I just render, that's what the render prompt does, is I want to like do the smooth version of the density field, for example, which in this case will show me column density because it's integrated. I'll probably have to adapt that. It's a bit useless for a shock tube, but it's the same principle for everything else. So I can see the smoothed field, which is what you would think about if you had like a grid and you were looking at this. Yeah. Make sense? All right, so that's the basics anyway. So that's Splash's job, is to do that smoothing for you. So it's not very interesting plotting a shock tube, but it shows you the code's working. So the only thing we want to do now is, well, here's one I made earlier. But for example, well, so Fazana's going to go through one with you. Maybe we can just break here and Fazana will go through a real example with you. Is that about right?
Now, or do you want?
Well, we should have a short break, right? So is there an official break time? Yeah, but that's all the mechanics of running Phantom. The only thing you would do differently, so if I wanted to run a general relativistic tidal disruption event, the only thing I'll do differently is write make grtdu make file, make setup make. So it compiles with, for example, gr equals yes, gives me the kerr metric. Everything works. It's pretty, one button that says go most of the time, not all the time, but things we've done a lot, they're usually pretty easy like that. So for example, like binary star interactions, this kind of thing, it's a one-stop shop, take your MESA file, map it in, relax it. It all happens. This will happen automatically, actually, in a TD. Reads the star, relaxes it, puts it into orbit. Off you go. So, so if someone's going to do an example, let's stop there. But I might just run this one just for fun, see what it does while you're having coffee. Yeah.
The quantum density with the overplotted solution, go through those options again.
Yep. Option 8 is the options menu.
Okay, so how do I do that?
O from the main menu.
Oh.
Number 8.
8?
Yep.
Okay.
And then number 3 is the shock tube.
Sorry, pause it. Letter O.
The letter O.
Or please configure selection now or option.
Get something splash.
Yeah.
0 star.
Oh, you haven't got files. You're in the wrong directory or something, or you haven't got any files. Should be in shock. Yeah. Yep. So O8.
Ah, there we go.
Shock tube. Yep. So yes. Press enter. And then just like 6 against 1 or something.
And then
Yeah. You pretty much just press enter from here. Yep. Yep. Zoom out a bit. Move your cursor and press minus a couple of times. Yeah. And S to save. And press space to play through your snapshots.
Very cool. Okay, great. Thank you.
Yep. So set multiplat. Also, if you want the pressure first, maybe you want that. It's in the D menu. Calculate extra quantities. Yep. Just press enter. Okay, so you got the pressure there. Yeah. So then multiply. Also, actually get used to pressing S now a lot. So S. So saves what you've done so far in these parameter files. Then M for multi. Yep, 4 plots is fine. Yep. No. Yes. So you want X is X. Yep. 1. Yep. And so you want like 6. Just press enter to that. 7. Yeah. 10. And yeah, and then just big M for plotting it. I'll press S to save again. The other thing you might want to do is just in the O menu, number 9. Yeah, just yes to that. And then number 2 is red instead of black. Yeah, just press enter to the rest. Just press enter. Just press enter. Ignore it all. Yeah. Save. Yep, now make your big M. Yep. Go. Press enter. And space 3 snapshots now. Yep. Yep. So if you just want to adapt your plot limits, okay, that's because you manually adjusted your gamma so you're getting the solution for the wrong gamma. So just press A inside the plot limits to adapt. A. Oh yeah, you are. Just zoom out a bit because you're just exactly on the limits there. Well, your exact solutions off the limits what the particles are. Yep. Save. Space to go forwards. Yeah. What are you doing? So your U is not changing, but your density looks fine. Your velocity is not changing. Okay. Oh, I know what you. Yeah. Okay. I know what we did. Sorry. So I should explain that. So in your
So Franco did this super high resolution, so we refine
If you do ls minus L, you'll notice that every 10th file is a restart snapshot, and the 9 in between are just a single precision, like smaller file that's just designed for making movies. So every 10th file has velocities in it and thermal energy, but the other files don't. So if you want to just plot the files that end in 0, so you just do like and then with a 0. So you just get only the restart snapshots that have the full information in them. So for example, so it worked for me because I was just plotting density. So density is in all of the small files and the big files, but the velocity and temperature are only in the every 10th snapshot. So they are updated, but they're just not spat out. So the idea, I mean, the number one thing we have problems with is you fill the disk with a heap of simulation data. So it's just trying to cut down the disk space by not dumping the full snapshot in. So you, and I guess what they are is like the big one is a restart snapshot. So you can restart the code from it. The other ones are just sort of visualization snapshots. Does that make sense?
Yeah, it's an unfair statement, right? Because they also aggressively acknowledge, so they actually push more grid cells that I have targeted still.
Yep.
I'm getting a ambiguous redirect when it calls on the line of the.
Can you just show us your Slam script?
Is yours also not submitted correctly?
No, it submits when it tries to exit when it tries to do that line to export.
No, I mean, like you get that it can't.
So that should be fine. So
Yeah, it's missing that.
yeah, because you haven't done the first bit. So you have to do the phantom setup.
Yeah.
Shock. You have to run it again.
Oh, there's a second time.
So so the first time generates the dot setup file, and the second time actually performs the setup. So yeah.
I think I ran it twice. I
So just ls in that directory? Yeah, so you did
shock?
because you got
Yeah.
the .temp and you got a shock.in.
So when I've been submitting it, I thought maybe like I had something in the wrong folder, but I kept moving things around. If you look at the
shock.1.log, yeah. Oh, you haven't got fancy. Oh, so you need to type make as well as make setup.
Yeah.
Just type make.
Do it again.
Yep. And then ls. So you got the phantom in there now as well.
Okay, I tried like moving things because I knew there was a phantom like 2 levels up, I think. But you just also need it here.
Yep.
Okay.
Well, so you want to so because we use a bunch of compile time flags, you want the phantom that's compiled for the problem you're trying to run. So you don't want like a generic copy somewhere else.
Yeah.
Yep.
Yep. I run my code with this one.
Yep.
I didn't
look.
I didn't get any output.
Let's see. Yes, that's fine. So SQ. Yep. So it's running. Yeah. So ls. It's because you haven't finished running the phantom setup. So you need to run phantom setup again on shock.setup. So just /phantom setup. /.
Oh, wait. Well, maybe after we need. Yeah. Well, we look at it. Yeah, according to. Yeah, right. Oh, yeah, same.
Both outcomes are kind of interesting. Yeah.
Well, we go to Eve, right? Yeah, after Eve, if we have time, we can probably look on what see if it looks interesting. It's hard to tell like pictures.
It's dangerous.
Oh, I was thinking just keep my.
How much time?
This one will be about 5 minutes. Yeah.
This is all, yeah, I mean, in my latest adjusted paper, it's actually pretty easy. That's the searching for Stephen Trudeau. Sure, very sound on set. Yeah, right now.
Is it S delete?
Yeah.
Oh, yeah.
So from there.
Oh, all right.
Sorry, we'll do that. Yeah, so we walk and look. Otherwise, you go another thing. It's worth a try.
Oh, wow. I don't want to mess up. I left the defaults good for Rusty so that when you get locals running it, it'll work. Oh, come on. Oh.
Somewhere. No, I use my
So don't tell Craig that I said 10,000. Probably on the.
Should have entered GR. Yeah. Easy problem. As I was going, just go.
I'm glad it got. Glad it's not.
That shows you some. Modify the vector Yeah, so if you just like update the so you can also type the source
Oh, 3 more years until 2026. Yeah, because you'll be starting fall in Arizona. Yeah, and he's fine.
Like lots of not right now.
They will all meet in Arizona. You ask Andrew about it.
Yeah.
This fall, October. I don't really know. Right. Yeah. So you'll so just you should attend. So they will meet for like. I wanted to go, but since I will be here, I might not be able to go.
Okay.
So when this.
Okay. Well, I can ask.
I'll go back home.
I'll
Come back here.
Harrison, is everyone in the room? Okay, so in this last hour, we might.
You won't because you'll be a student there. I
No, I haven't.
Is this on now?
Yes.
Yes. Okay, good. Okay, right. So in the last hour, what we're going to do is we're going to use Phantom again, and we're going to run a simulation or a couple of simulations of self-gravitating disks, right? I showed you 1 or 2 movies of these this morning. What I'll do firstly is actually just talk you through some of the physics of self-gravitating disks, because there's no point in running a simulation if you don't actually understand the physics, right? So I put this slide up this morning in my talk. I was talking about the star formation process, the disk formation process, and eventually that leads to planet formation. So this was this very early stages of the molecular clouds collapsing and the disk forming with the star at the very center. And this phase is actually where the phase in which you will get self-gravitating disks, right? So these are disks that are very massive. They're so massive that their self-gravity essentially drives the evolution of these disks. The reason why I chose self-gravitating disks is that although I look at these on the protoplanetary disk scale, they actually, self-gravitating disks actually exist on a number of different astrophysical scales. So hopefully some of you will come across these at some stage in whatever kind of area you're focusing on, right? Where was I? Right, okay, so we've got these self-gravitating disks. Because of the way they evolve, essentially you see these really characteristic spiral structures forming, right? If the conditions are favorable, then you might actually get fragmentation happening in the context of protoplanetary disks. We might think about this in the context in terms of sort of planet formation or even brown dwarf formation. And there's your little fragment in this disk, right? So I'll just show you 1 movie of these. Gosh, this is from sort of a century ago or something, a decade ago, where you've got a a self-gravitating disk evolving. Eventually, what you'll see is that in the outer parts, the spirals become unstable, and I'll talk you through the physics of this in a minute. They become unstable, and eventually they fragment into these little gas balls, basically. So, how do you actually describe the stability or instability when they fragment of these disks? Well, we have this what's called the tumor parameter. Essentially, it comes from I should have a citation somewhere from Tumor in 1964, I think. And that interestingly, that paper was not about protoplanetary disks. That was actually about galactic disks, and it was talking about the stability of stars in the in a galactic disk. What you have is this tumor parameter, which is Q, and that is dependent on so essentially a region in this disk. You can actually think about the forces that are at play in this disk, right? You have pressure forces which act to stabilize the disk. You also have rotational forces which also act to stabilize the disk. Now, pressure forces and rotational forces are both the stabilizing parts of this, but actually gravity is the part that actually causes the disk to destabilize. And if it's pressure acts on very small scales in the disk, rotation acts on very large scales, and if those scales don't overlap, you actually have this region in between where the gravity forces become more important, and they can actually cause the disk to destabilize and fragment. Right. So the condition that we have for an infinitesimally thin disk, we're not quite dealing with infinitesimally, well, we're not that thin a disk, but this is broadly, we can still use this. The condition is that if this Q value is larger than 1, the disk is stable. If Q is less than 1, the disk is unstable. So this, we will plot these stability parameters once we run some simulations, so that's something to bear in mind. Here we go. Sorry, this is actually the reference that I couldn't remember if any of you wanted it. So we're talking about Tumor in 1964. Okay. Right. Okay. Now, self-gravitating disks have what we call a thermostatic nature associated with them, right? The images I'm going to use here are a little bit exaggerated, but just to sort of highlight a point, right? If you have a high tumor value, this disk is very stable, right? There's no heating in this disk. What's happening is that over time, this disk can actually cool. And as the disk cools, it starts to get to a state. So here's where the cooling plays a part, right? In the sound speed, that's the temperature in the disk, right? So as the temperature goes down in the disk, you start to get towards a Q of 1, right? Or anything less than about Q of 1.7 is when you start to get these spiral structures forming. Now, these spiral structures are regions of shocks in the disk, and shocks are, of course, parts where you're actually heating the disk, right? So those shocks will actually lead to heating, and you'll end up back towards this state, right? And then the cycle sort of continues, and you have this nice, what's called a marginally stable disk, right? The reason why I said it was a little bit exaggerated is that you never actually get to a stage where you completely lose your spiral structures. This is just for the purposes of illustration. But essentially, you stay in this marginally stable state, and you have a disk that looks like this. However, if you can do something to the disk to actually overcome that thermostatic nature of it, then we can actually start thinking about fragmenting the disk, right? So what we often do, it's not physical. This is just a parameterized way of thinking about the cooling in the disk. What we often do is to say, right, let's define this beta value. This will be important for these simulations that you're going to run. Okay, and that is essentially a dimensionless cooling parameter, right? It's a cooling time in units of the orbital time scale, essentially, right? So here's what we know from a couple of decades ago, that we need to have the cooling being faster than a critical value in order to get the disk overcoming that thermostatic state and ending up in a state where it can actually fragment, right? And typically we've got this number of about, that the critical value is about 3, right? So this is what we're going to actually think about with the simulations that we're going to run. So what we're going to do is run a couple of simulations. My suggestion is sort of beta of 3 and beta of 10. Pick whatever you want. Just have a go, right? You might want to do this in pairs so that one of you picks a high number, one of you picks a low number, just for the sake of just to make sure that you can see the output. So in the next hour, but feel free to run as much. Well, I'm not sure as much as the Flatiron Institute will let you run, right? What you can do with Splash is to look at very easily. You can look at this tumor stability parameter. There's an option in which I'll show you in Splash to be able to plot this. We're going to try and make some movies if we can, right? We'll produce we'll at least get as far as producing the images using Splash, and then you can use your favorite kind of combining, movie making technique to be able to actually make one of those movies that I showed before. And actually, here's one that Daniel prepared earlier. What he has is the self-gravitating disk here, and you've got this tumor parameter that's against radius that's just changing over time as the disk is evolving. Okay, right. That was a really, really quick tour through self-gravitating disks. Here's the actual practicalities. We'll do this together, but I'm going to walk you through this. So this in the background is Daniel's notes on how to actually run a simulation. What we're going to do here, okay, so we're going to look at this part of, I'll bring it up and we'll look at it together. Essentially, the main differences are you just need a new directory, whatever directory you want to call it. Instead of the setup shock, you're going to use the setup SG disk. That's a self-gravitating disk. The next couple of bits are exactly the same. We need to set up, we need to produce the executable that sets up the disk. And then we're going to produce the executable that sets up Phantom. And then what are we going to do? We're actually going to set up the disk, right? And this is actually the bit that we'll do together, because there's a few aspects that I'd like you to change. And then whatever you actually call this bit, it doesn't really matter. You called it shock before, you could still call it shock if you want to. You just have to make sure that you use the same name here. Okay, let me come, I'll show you this again. We'll do it together. Let me come out of this presentation. We'll come into, where's my, so let me see if I can bring this through here. Oops. In fact, sorry, bear with me. I'm going to actually, I've just realized this is not going to work very well.
Factorial, like tomorrow, like by the end of the stuff, by next Friday, it's like 300 times out of the to keep it running count. And you just start to want to.
Okay. Hopefully this should work. However, oh, that didn't like it. That looks good, but I've lost my I've lost my I've lost my instructions. Here we go. Where no, it wasn't that one. Okay, let me unmirror it again and let me see if I can just find those instructions. Sorry, apologies. Okay, let's bring this back up as well. Oops. Oh, it's hard to do this when you're looking the other way. Here we go. This is better. No, no, I didn't like that. Something happened. Sorry, bear with me while I try and navigate this. Okay. No, it left the rest of it there. Okay, here we go. This works. Sort of.
What were the options? Oh, yeah.
Can you see these? Is it big enough, or is it? Do I need to just make that a little bit bigger? Okay, right. So hopefully you're all on Rusty. If you make get rid of this. There we go. Okay, right. So we're going to make a new directory. You can call it whatever you want. I'm just going to call it SG disk. And we're going to follow essentially, these are the instructions that I had said we need to follow, but we just need to change one or two things, right? So you're going to link to your phantom write make.sh file, right? This is essentially what we want to take. I'm going to just modify that a little bit for me because I've just got it in a slightly different directory. And what you want to do is for this bit that says shock, that looks tiny. Can you guys see that at the back?
That's better.
Is that better?
Yes, please.
Okay.
Could you raise the bottom of the window up a little bit? Yeah, perfect.
Does that work?
Yes.
Okay. Right. So instead of shock, you're going to use SG disk. Okay. Right. So if I do an ls on that, you're going to see that there's a make file exactly like there was before. We are then going to make the phantom setup. Should take about a minute. That was exactly the same as what we did before, except this time it's running the SG disk rather than the shock that we did before. You okay? Whoa, really? SG. Oh, disk with a C. Yes. Sorry. SG disk with a C. Is that how do they do it? I'm not sure how they write it in Australia. UK, definitely with, is it with a C? Okay, there you go. Right. So SG disk with a C. Once you've set up your, you could actually do these in either order, whether or not, so here we go, you've got your make setup here. That's what I've just done. I'm now going to do make, but actually before I do that, I'll just quickly show you. This is once you've done your make setup, that's your Phantom setup, which we're going to use together in just a moment. But let's set up the Phantom executable. This is the bit that's actually going to run the code. So just type make, and that should produce your Phantom executable. Okay. So hopefully that's all still familiar from Daniel's session before. Right, the next bit is to actually set up the disk, and there's going to be just a few additional steps compared to what Daniel did with you before. So we're going to do this /Phantom setup, and then you can call this whatever you want. Daniel called it shock. You can still call it shock. I'm just going to call it disk. You can call it disk with a K. It's not going to either way. And what it's going to do, I'm just going to try and expand this a little bit, but just to show you what's going on here, right? So it just gives you a little bit of an introduction, a little bit about the fact, telling you that you're in the disk setup. This is actually a really nice interactive setup so that essentially it's going to set up the disk how you want it. So the first thing it's going to ask you is, do you want to use sync particles or an external potential? We're actually going to use sync particles here. This is going to be the central star, okay? So we just leave it as a default. We can go through that. How many syncs? We've got 1 star, so we're going to go with 1 sync. Am I going too fast? Have I lost anybody? Okay. Good. Sorry, was that a yes, I'm going too fast, or I'm okay? Okay, thank you. Right. How do you want to set the gas disk mass? Typically, actually, let me move this up so that you guys at the back can see it a little bit better. What we're going to do in this case, there's a number of ways in which you could do this, and you can actually see that Phantom's really quite versatile in terms of sort of all the different setups. It's almost like someone's thought through all the different ways you might want to set up a disk. What we're going to do is just go for the default. We're going to go with the total disk mass. Do you want to exponentially taper the outer gas disk profile? This is basically saying, do you want that surface density in log sigma, log r space to drop off? Or do you want it to drop off and then taper towards the end? We're just going to go with the default of no, it's just going to drop off, but not taper at the end. Okay, do we want to warp the disk at some stage? Maybe you might want to. Right now, I would say no, let's keep it simple. So we're going to stick with no. Do we want to put planets in there? At the moment, I'm also going to say no. We want 0 planets. Enter the time between the dumps as a fraction of the outer disk orbital time. We can stick with the default on this. This really, you'll probably want to think about this when it comes to kind of producing really, really nice movies. Okay, enter number of orbits to simulate. Right, this is going to give you a lot of dump files. Let's just change this to, let's change it to 5, because you get 10 dump files. Oops, 10 dump files per orbit, since we're going for a default of 0.1 for the fraction here. We're going to get 50 output files. Even 5 orbits will probably be too much. You'll get the idea of what's going on with these simulations pretty quickly. Okay, then very helpfully, Daniel gives us a reminder that we have to write that we need to edit the disk.setup file. Okay, if I just do an ls and show you what's happened, right? All that's happened here is that we've got this disk.setup file. Let's look at that. So you can do that with your favorite editor. I'm just going to expand this a little bit. What we're doing, there's a few things I'd like to, let me expand this way. there's a few things I'd like to just ask you to change here. The first is the resolution. This is going to be incredibly slow if we go with 1 million particles. So I would go for, I'm going to change mine to 250,000. I ran that yesterday. That was reasonably okay in terms of how long it took. Then you've got various things. So again, right, we specified that we wanted to use sync particles, and we wanted 1 sync particle. You could actually go, do you know what, I made a mistake with that. Maybe I do want 2 sync particles, and then you can change this. Right. We're going to keep the star mass as 1. We're going to keep all of this the same. We are going to change things a little bit here. The outer disk radius, we're going to change that to 10. Otherwise, we're just going to have a really, really poor resolution. The disk mass, let's change that to 0.1, just so that we can get these spirals forming quite nicely and strongly. And then I think that's probably all I would like you to do in that case, right? Okay, so the only thing you've done is to change the resolution, the outer disk radius, and the there was one other thing we changed. We changed the disk mass as well. Okay. Good question, Daniel. Reference radius.
Okay, so the reference radius
It's not
is
relevant.
the radius at which you want to set, for example, the H&R. So you want to set the H&R, so H&R depends on radius. So you want to set H&R at some radius, and that's the radius at which you want to set it.
We probably don't need to worry about it too much for the simulation, though. I think
you got a temperature that goes like, so the temperature goes like R to the minus 1/2 here, because the sound speed goes like R to the minus 0.25.
That's this bit.
That implies that H&R, you have to fix the temperature at some radius, and so you're fixing the temperature at R equals 10.
Yeah.
Which you'll see in the bottom, once you run this, you'll see it in the bottom printout.
Yes.
T equals something,
So
R over 10 to the power of minus 1.
So we will probably actually, I mean, this is these are scale-free simulations, but actually what we could, you could change that reference radius to 1 actually, because that probably, yeah, that probably varies. Otherwise we'll have a really, really thick disk. So, okay, so change that reference radius to 1, sorry. Okay, we're good there. Did everyone follow? Oh.
Can you change the particle MP at the top?
The number of particles, yes. Change that to about 250,000. Yeah, 1 million will take far too long, and we won't finish in the next half an hour. Okay. Any other questions? Is everyone still with me? Good. Okay. So we've modified our disk setup, but let's see, where I'm sure it was here. Here we go. Please edit the disk setup for your problem, then rerun Phantom setup. That is the important thing, because we modified the setup, so we actually need to rerun the Phantom setup. So here we go, Phantom setup, and then disk again, whatever you called it. And then here we have a bunch of things that it will print out. You can go back and check these if you would like, but you're basically, it's just telling you a few things that you've already kind of included in that file, a few relevant bits of information about resolution. Then these are all the parameters that we'd included, but some derived parameters as well. And I suggest we kind of look at these later on. You have a look at these in your own time. And then, most importantly, we've got a couple of files that have been written, right? You've got your disk.in. This is your input file for Phantom. You've got your initial temporary file that's produced, which is basically the dump file that's produced. And I think that's largely there's one other file, the disk.params, but I think disk.params, but that's not so relevant for this just yet. Okay, let me put this back up so that you can all see it. Here we go. let's go back to Daniel's instructions. We then go back to this script. You can copy the script that you used before, or you can just kind of make this new script. Just remember, you need to change this this name here, the in file. It's disk.in for me, and whatever you choose to call it. And then here we go. This is what we've got, and we're going to run this on the is it the temp partition? I don't think there's anything here that we need to change.
Shouldn't be, sorry.
No, I think you've set that. Oh, sorry. Do you want that back up? Or were you about to say something?
No, so I mean, this, you notice this email address, for example, got done automatically. That took it out of your, when you type git config, my email address, that took it out of that.
Daniel's watching us. That's basically what's happening
As long as
here.
it's creeped out, because I mentioned, you'll see in a minute. You'll all be creeped out.
I was creeped out by something. Okay, right. That's it. I think we're good to go, right? So here we go. This is the just a reminder, that's your command. Hopefully you know and love this. Sorry. Good point. Good point. Okay, so sorry. Very, very good question. It's in your disk.in. Actually, let's take a look at.
So there is a page describing all the parameters in the value file, which nobody has ever read.
Okay, that's a very good point, actually. So here we go. This is basically saying that your log file, so you had your shock01.log before. This is basically what your log file is called. This is a temporary dump file that's input into Phantom. We've got a whole bunch of parameters to do with the timing of the simulation. We won't go into the details of these, we won't have time, but there's you know, as you get more and more into Phantom, you can kind of look at this a little bit more. Hopefully you recognize the current number. That's one to that's here.
You're asking about that before.
I can't remember if you covered this morning. Did you cover one, the HVAC? That. So we'll leave everything else the same here, but the cooling, Jess, you were asking about the cooling side of things. This is your beta cool. This is your value of beta that I had in my presentation before. This is the one where I said, let's run one with 3, one with 10, choose whatever numbers you want to see what happens, right?
Sorry, what is beta by itself with no underscore cool?
Aha. Artificial viscosity. To
No,
you.
it's not artificial. It's
Oh, well, it's not.
shock
Sorry.
Non-linear shock capturing parameter.
I come from a decade where we called it artificial
High resolution
viscosity.
shock capturing parameter beta. So if we start saying artificial viscosity, everyone thinks it's all bad and wrong. So instead we're going to call it the high resolution shock capturing nonlinear parameter beta.
Go ahead. Okay, so you can change this parameter to whatever you want to, right? These are those sort of two numbers that I was saying. Let's pick one high, one low.
I'm looking through the file.
Okay.
It says like 30.
Is everyone with me still? Yeah, we're good to go? Okay. So back to Daniel's instructions, we're just going to do this, right? SPH -p temp run.q. Okay. And there we go. We've submitted it, actually. Sorry, let me put this high up again. Oops. Okay, so hopefully we might just have to
I discovered someone had this like -me command for SQ, which is kind of cool. -me.
minus me, like that?
Yeah.
Oh.
It's one thing I learned today.
Oh, good. That's really handy. Okay, it's not started. Oh, it has. There we go. Right. So what you'll see, in fact, I'm just gonna, you're gonna,
a couple of these files as well. So there's a couple of extra files we didn't discuss. So the log is what would normally go to the screen. That's the simulation output. This EV file contains like a bunch of kind of global quantities that you should check. So for example, total linear momentum, total energy, total angular momentum, various other things as a function. It's just a simple ASCII file with column labels. You can plot that with Splash as well, but it's just a simple ASCII file. But so you can look at these things like that. So these are global quantities, so there's one per simulation, right? But it shows you as a function of time. And the point of this file is it's very frequent in time. So basically every time step you get a number in this file. Whereas obviously snapshots are much more, what's the word?
Infrequent.
Oh, there's one more file there as well.
Let's have a look.
Which so we have a sync particle in this simulation. So a sync particle is a point mass. And so every sync particle, you also get a file with very frequent information in it. And then it has positions, mass, velocities of that one particle, because it's the special particle, which is the point mass.
Great. Okay, so you can do a whole load of sanity checks basically to make sure that things are being conserved, etc., and doing what you expect them to. Okay, right. If you run a simulation with a low beta value around beta of 3, probably in about 20 minutes time, you're going to see some kind of fatal error. This is basically because the particles. The disk will actually fragment. The particles will get really, really close together, or some particles will get really close together in the parts where it's fragmented, and the time step becomes incredibly, incredibly short. It's just going to grind to a halt, right? So you will, let's actually look at the disco1.log file. What you've got it's just all the header stuff. This is basically all the information that we put in. We can go through, you can double check, you can see that here we go. There's my cooling. I went for 3. Let's see what else we've got below that. And then I think everything looks pretty similar to what you will have seen before with the shock example that you did with Daniel. Again, oops, sorry.
The units will be different. So units are actually helpful here.
Oh, that's right. Yes. Here we go.
Well, it's still sort of dimensionless because you have a dimensionless cooling rate. So you could still interpret this as a galaxy, I guess. So we're just here. If you want to interpret what one unit of length is in the simulation, that's that length scale, which is an AU. That's 1 unit of time in the simulation. Yeah. So Splash would use those units automatically for you, but remember the actual simulation outputs are always in code units, which is dimensionless.
Yeah. Okay. So then you see that actually you may or may not have spotted it, but we had this disk 000. It was a .temp file. That temp file's been deleted. It's now been overwritten by this actual dump file.
What's the difference to the audience? What was the reason for the .temp file?
All the density out there.
Yep. Good. Maximum regionality.
And then you've got some really, really useful information about the time stepping. So I have no idea why this happens to me every single time. But anyway, something happens with my formatting. Okay, right. Useful stuff for these simulations is actually, with this particular one, especially because it's going to grind to a halt, bear with me 1 second, is just to look at how long it's taking for your particles to be moved, right? These particles are all on, I'm not sure if that was the same for the shock test, but these particles are all moving on individual time steps, right? Those ones which can be moved on larger, with larger time steps will be, but and that's the advantage of this, that you don't have to move everything, all your particles on your smallest time step, right? So you can move some of them on the big time step. You can move the fraction that are in sort of this dense clump to on a much smaller time step. And then you'll see that over time, actually, kind of you do actually end up with smaller and smaller time steps as this simulation progresses. There were a couple of questions. Go ahead.
I was talking earlier, but what was like why do some particles fail to create? Like, is it just because they happen to be unbounded that you just like fly off, or because when you go through the simulation towards the end, you have like a couple hundred particles that end up
failing to accrete onto where? Onto the sync particle.
So I think the question was about this thing here. So totally accreted, but some point it tells you like.
Oh, should I go up?
Particles woken. I think there's.
Where am I?
It says like how many particles failed to accrete.
Oh, oh no, that's the top. Let's see. Let me look for failed.
Can you go back to the .in file? Because there's something important here, which is actually sort of badly described in the in file. But in the options controlling sync particles somewhere.
Sync particles, here we go.
Okay, so there's a factor here which is 0.8 by default. It's actually kind of important, but basically sync particles are more clever than just deleting everything that crosses a radius. So there's a hard boundary and there's a soft boundary. So the soft boundary is eat everything that crosses the radius and satisfies a bunch of conditions. And that is by default 0.8. So 0.8 of that is the hard boundary. Yeah, so if you go within 80% of the sync radius, you just get swallowed, no checks. But this, I mean, this is meant to be an adjustable parameter. So that's what it means. It means you came within. No, I don't. How do we look at the sync radius here? Actually, a real simple way is, well, it probably was in the file, in the log.
Let's have a look. I think it was just one.
Well, so you did set it, obviously.
Yeah, I think we just set it to 1, if I remember right.
There should already be some output telling you what it is, regardless of what you thought you said.
No more.
It'll be in the dot setup, but we'll just keep that in. Here it is. So there's an accretion radius here.
There we go.
The table, which is 1 AU in this case.
Did that address your question? Okay, great.
This may just be personal problems, but all my jobs keep getting canceled and nothing. But
Oh.
I could try like logging out and back in.
I have a problem where you can't run more than one, so you've got other things running.
Oh, I do have two running up there. Maybe that's I can get rid of that. It's like. Mine's not running either. Is yours getting canceled? Is yours still? It doesn't even stop. Yeah, mine. What does it say when you see the queue? Does it say? Is there in the when you? I think the notes say here, but then he does like.
I have so much.
Yeah. When you do the SP is that like right now?
Yep.
Just have a look in this study.
Let me come around.
Is that the simulation data equals 3 should crash after about 20 minutes or so?
Yeah.
What about the data equals 10? Do we need to like
That will
stop that? Or?
That will stop after you've got to about 50 dump files. That will stop. So yeah.
It won't, because I know the setting on the slurp was like really high.
Oh.
I didn't know if it was just gonna keep going.
Yeah, no, it won't keep going. It will stop, and you'll see at the very end. It will tell you that it's finished nicely. So what we can do. Oh, sorry, hang on. Are people still trying to run this simulation. Have you managed to submit it to the cluster? Yeah. Is it just two? Okay, what we'll do is we'll try and sort out these two, then we'll try and splash these, and we'll have a look at them. Are yours still not running?
Yeah, I think if you just try that and then see what it outputs on the command line. Oh wait, sorry. Do srun dash p like 10 and maybe dash c like no more than 10. Just trying to see. Or even just do one just so that we're sure that that's not an issue.
So you can go ahead and splash these files before it's finished.
If it doesn't, if it cancels, then it should at least tell, like, say why, right? Yeah.
Yeah.
Like Google,
Let me ask Daniel if he can come and help you with this one while I continue. If it's okay, but I can still go through the Splash stuff. I mean, you're familiar with Splash, aren't you? So, okay. Right, we're just having. Do you mind helping Caitlin while I continue taking people through? Okay, so yeah, indeed, like Daniel said, you can actually look at these files as they are being produced, right? So we're going to splash disk. I'm just going to open all the files. So this is going to open 8 of them, and what this all looks pretty similar to what you saw before, except we've got slightly different. Do we have different variables? I can't remember. No, I think they're pretty similar. These are the same variables, right?
So just one thing here. So at some point in the recent past, I decided to make it look easy for you by like trying to convert everything into physical units already. But you should remember that underneath everything's just in code units, and so Splash tries to guess by the name of things what the unit conversion should be, but it sometimes gets it wrong. So these things are all okay, but sometimes if you've got extra columns, the unit conversions won't necessarily be correct. So you can use minus code to get, if you just do that again. So what used to be the default was minus code here. You can also do it from the D menu. Yeah. That just gives you everything in dimensionless units.
No.
That happened by default for you for the shock tube because it recognized the units were all 1, and that's a dumb thing to use. But so by default, if you do have physical units set, it will try to use them, but use with a little bit of caution because underlying that, things are really in dimensionless units, and it's just tried to guess what the conversions are. Yeah.
It's probably the options.
Yes, in the D menu. Like you say, physical units, so we just switch them off if you press 2. So these are the numbers that it's tried to guess for you. So this is the conversion to AU from code units. So we were in AU, so it's just a multiply by 1. But for example, the time, it's multiplying with this crazy number. This is the multiplication from code units into ergs per gram. So just apply a little bit of caution with how you interpret these things.
I'm going to say no for this, just because I prefer working in code units. So okay, right. So what you can do here is, well, we can start by doing what Daniel did actually. What we can do is just look at the disk to start off with, right? So my y-axis, I'm going to go for 2. I'm just going to plot x against y against x, and I'm not going to include any rendering. We will come back and include some rendering. Let me bring this up. Sorry. And what you should see in a second, or a few, it's plotting quite a lot of particles. So it's going to take its time. So I won't do this for every single.
So interactions won't work through the Jupyter.
We did minus 5, but yeah, we can try again.
We can.
So you have to minus y into the gateway and minus y into the rest.
Yes.
So I'm actually going to. Did yours pop up? I think I'm kind of regretting bringing this up because it took some time. Okay, these are basically all your particles, right? Sometimes it's useful to see the particles. What for the disk, it's actually more useful to be able to sort of render it by temperature or by density. So when you've got something that comes up, if you just press Q, you can just get rid of it, and we can do this again. So if we plot Y against X, but this time when the rendering option comes on, pick the column that you want to render it by, right? So I want to render by density. So I'm going to write 6.
By default, this gives you a projection, so it gives you a column density.
That's right. Good point. Yes, you can do slices as well if you need to. Vector plot, we're just going to default 0. Graphics, this /XW basically means that it's going to plot it to the screen. If you want to produce movies, right? If you just press question mark, you can actually see all the different options, right? So you can actually plot them as PNGs, whatever, PDFs, SVGs, whatever you want, right? And essentially, then you can then stitch those images together and produce a movie. I'm just going to go for the default, just so I can show you on the screen. And what you will see is that it comes up with the disk rendered by density. What we're going to do is to actually bring your mouse onto the color bar and just press L, and that's going to change that column density from linear to log scale, right? And then as you move through each of these files, so just press spacebar to go through them. That's the initial disk. We should very soon see. That didn't happen before. That didn't happen before. What happened? Okay, so you can go back onto your color bar and press A, because that will then bring out the whole range that you're interested in. And actually, you can zoom into a particular part of the color bar, and this will hopefully bring out the spirals a little bit better. Remember to press S once you've done that, so it saves your limits. Actually, let me bring this on this side so you can see what's going on the left-hand side.
What's the command to produce that image? Sorry.
Sorry, the command to produce the image?
Yeah.
Let me do it again. Okay, so we want to plot Y against X, so 2.
Splash, and then it's.
Oh, I'm sorry. Let's go there. This is the command, splash.
You guys don't need the minus code.
You don't need the minus code. Indeed, you can. You can leave that out.
Just be careful with the number of zeros there. So we're only going to put the first 10 files through them.
That's right. I didn't have too many files at that time, but actually now I do. So I'm just going to change that and get rid of one of those zeros. Okay. So did you get that?
Yes.
Okay. Fantastic. We're back in. We're going to plot Y against X. So 2 against 1.
So in fact, if you just want a shortcut, you just Control-C for a minute. So shortcut to what Fazana just did is a -R6 or -R density.
Minus where?
Just there. So if you want to avoid the menu altogether.
-R6.
With a space. Or you can just give the name of the column as well. Yep.
Is that good enough?
Yep. That'll just take you straight.
I would never remember that. I'd much prefer an interactive menu, but yeah, probably I can see how that would be useful actually.
Sometimes the menu gets annoying. It's possible just to skip straight to that show.
Okay. So this time round, it's actually remembered my the fact that I'm asking for log scale, presumably because I pressed S to save the units, so it saved it in this directory. And then what you can do is press your spacebar through, and it will go through each of the files one by one. Whoops, what did I do here? There we go. Okay. what you can do is actually, you can skip through many files. So if you've got, hundreds of files, you can actually look at every 10 or every 100. But I'm just going to skip through these one by one.
Has everybody got a plot like this up? Stands up if you have it, because I'll come around. Nope.
Terminal issue we're having is about the It's the same, like, is the error coming up next?
You know the last command.
What is it? Sorry.
X4 working.
I was going to ask you if you did the -y at the very beginning.
We did, but we found out from Maria that maybe well, we thought it had to do with like like I would think that's in before.
You have to install this.
Oh, I don't know that. That's okay. I'll just download the file.
You can just like now do a PNG and copy it.
That's what
You
I
can
was just
indeed, so you won't be able to see it on your screen, but then indeed you could, oh, right. Good point. Sorry. Yeah.
But like IE did like 25,000 particles, so it's like very low resolution. But yeah, so it looks like very like fuzzy.
What beta value did you use for this?
I think 2.5 or 2, something like that.
Yeah, so maybe probably you can kind of see hints of some of those spirals there, right?
Yeah. I just ran it really quickly just to get something.
Yeah. So did you see it fragmenting at all?
I don't think I did.
Okay, that's fine. That's fine. If you up the resolution, you probably will see it fragmenting.
I'm having a I'm actually doing some wrong, but anytime I make an event, either RC or.
There's a way to do that.
Oh, okay, that's fine. Thank you. I was like.
So if you run, so this is my simulation with a beta of 3 with 250,000 particles. You should, this is after, this is dump number 15. If you ran that exact same one, you probably will see something that looks like this. If you change your resolution, as you've just found here, you might not quite see the same thing, but that's okay. Look at my 2010 paper and you'll understand why. The resolution does make a difference here a little bit.
So, Razan, do you want to take everyone through the important bit?
What important bit?
Press enter.
Oh, press enter. This is the really cool thing that I found earlier. Okay, so just be on your image, I think, and you just press no. Yeah, you just be on your have your mouse on the image, press enter, and then this happens. Look at this. Somehow, freakily, Splash knows who I am. I don't know what Daniel's done. I have no idea how this worked, but this I accidentally pressed enter earlier today. That's what happened.
Wow.
Yeah.
It's interactive.
I don't know. How do you do it, Daniel?
I think you can drag it.
How do I find your name?
How do you find my name?
There's a Unix command somewhere.
Ah, right, okay. So you can produce nice images like that. If instead of printing it to the screen, remember, instead of /xw, you do /png or whatever other image files, you can actually produce a movie after that. How how did you manage?
Oh,
Oh,
it looks yes. I just have to rerun it for the rest of them.
yeah. Okay. Okay. So you're starting to see spirals here, which is really nice.
I did
That's
the factor
lovely.
of 10, and I'm only at the third out.
And if you you're plotting all the particles. If you render it by density, that's how you're going to get the what you see on my screen. So if you do 2 y against x, just like you did before, so yeah, 2 and then 1 for your next one, yeah. And then at this point, you want to say, so the default is that it will just plot the particles like it has done there. However, if you press 6, you can also do it by temperature. You can also do it by anything in turn. This is the internal energy, I think. You could basically kind of produce a map of the disk with that parameter plotted. So yeah, if you do 6, that should.
So capital Y is the same as minus capital X. There's some small difference that I can't remember, but it works better most of the time.
And then yep, default. And then
okay, and
so
I'll do a PNG.
if you do, yeah, exactly.
Thank you.
Now it might be that we have to play with your limits, your color bar limits to really get it right, and we can't interactively do that here. But let's see what it produces. Yeah.
Sorry, the command to open splash.
Oh, it should just be splash.
Sorry,
And then what are your files called? Disk. Okay, right. So it's splash, then it's disk. Exactly. Yeah. And then there was if you wanted it to be in code units, and it's minus code.
Oh,
look at that. Now this is in log scale. Now how do we convert it without doing it interactively? There is a way of doing it. What you can do is I think you can change some of your variables so that they are in the menu as if I just show you.
So if you want to make a movie, I mean, because I'm going to do that, there's a one-liner basically after you make your PNGs.
I haven't done that here. I always do.
Same thing again. So 216. Then just PNG at the front. So that generates your image sequence. Actually, we're using a large number of CPUs by default. Probably a bad idea if everyone was on the head node. You might want to put export OMP non-threads equals not 32.
Oh.
You're not all trying to render at the same time. Oh, yeah.
It's coping.
Yes, it is.
Was there a good way to view movies?
Yep. Yep.
Do we have to see it down? Or
well, so probably you can do it in your Jupyter thing. You really want. But you want to make MP4 first.
There was someone the other day doing a demo. He was trying to show us the movie. I can try. I put it yes.
I did.
So there's just something here that we just need to do to make sure you get to log density rather than density, and that's the thing. No, that's fine. Yeah, if you bring in what, yeah, could do that, and then we can see. In data. Yeah, if you just do, let's have a look. No, that's not it. I wonder if it's one of these options. I wonder if it's either limits or options. I'm not quite sure. Oops. Yeah, let's come out with that. Let's try limits. Look. Let me just see if I can figure this out.
Applying log other transformation to columns in limits. Is that the
Oh,
right-
that might be.
So it's fine.
Enter. Oh, no, 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 enter is like this priest.
Yep, so try, I guess try 6 for that.
Oh, I see.
Oh. Oh, yeah, log. So if you want log, then it's 1. So, yeah, that one's 6. You've already done it for 6, so now we can just quit. So you can type 0. So, and then log, yep, so number 1. And then, so now it's your 2, because we're going to plot y against x. So it's 2 against 1. And then you're going to render it, yep. And then, yep. And then this is your PNG again. Oh, where do we get to? So this, yeah, we're just going to quit. Yeah, so we've done, and so now see your density is log density. So that was definitely the right, because now you can see so now it's again y against x, so it's 2 1. And now it's just, now it might, the only issue here now is that we might not get the limits right. So, but what we can do is to then go back and you can, there's the limits menu, we can go into that and change the limits. Yep, okay, yes, I've produced the PNGs. What next? Do you want to?
Oh, we got PNGs. So there's a one line that you just need to find in the Splash documentation and paste. So moduloid FFmpeg, because you say FFmpeg is just the command line tool that converts PNGs into a movie. And there's just a magic bunch of options you need. There's a script in the Splash directory, but you don't have your own Splash installation. So we need to find the documentation.
Do you want this? Do you mean the Splash documentation?
Yep.
It should be in my. There we go.
So in Splash documentation, there's a thing called like basic Splash usage or something. There's like Hollywood mode. There's producing a movie from a sequence of images. And there's a magic line, which is 2 lines above that, just that one there.
Oh, 2 lines above it.
Yep, you're right on it. Just below.
Oh, sorry, just
done that bit. So that's just copy and paste that line. It's just a good sequence of defaults for FFmpeg. So in particular, well, let me just explain those options for a second.
Oh, which ones? Back here?
So basically, we want a pretty slow frame rate, so as slow as you can get. We want a high data rate, so the movie's good quality. The pixel format is just a little annoying thing. So you'll notice like sometimes MP4s don't play in Slack, for example, or don't play automatically. That's because, like, for example, in Slack, they only play MP4s if they're in this pixel format. So the annoying thing is, so for example, MP4 in that format has to have an even number of pixels, for whatever reason. But then, so this one is just slow the movie down by 4 times, which is usually what we need. If you're in Z shell on a Mac, you have to backslash the star here, and that's the name of the output MP4. So if you just paste that in, usually that just works by default. And there's a Splash script which just executes that command. FFmpeg command not found means moduloid FFmpeg.
FFmpeg.
Do it again. Okay, so that converts your PNGs into a movie, and you should have movie.mp4 laying around.
There we go.
So you can copy that back, or you can
download.
I think you can. You can maybe play it in Jupyter Lab or something.
It doesn't play in Jupyter, but you can right-click download from there.
And there you go. That's your first Splash movie.
But before you make your movie, you should be in Hollywood mode. I don't want to see movies with white backgrounds and text.
Oh.
Oh, I don't interact.
We've been doing everything.
That's okay.
Okay.
I'll get
Let me give you some limits. Let me give you some limits to choose. Well, we see we're not interactive.
Our house, you guys would
We're not interactive here. That's all.
I'll try again. I don't have the whatchamacallit installed. I do have it, but it doesn't work.
So you need SSH minus Y both into the gateway and into Rusty.
Try, let's try again.
First of all, you can check your expert as well. Yeah, not on Rusty.
Oh,
just
type no, it in. No, I don't have extra. That's my problem.
Quick question. Was your were your units in code units or were they in or were they in?
I think they were in code
units. Okay, let me give you the code units.
Sorry. I think I didn't manage to get the interface just yet.
Oh, okay.
So Express is the Linux known system.
Free version from the or from the interactive.
So if you try setting your limits to between sort of -5 and 0, you'll probably be able to get the X. Are you doing the X? Okay, right. It does make sense.
Was that for 3? Wait.
This was a beta. Sorry, this is a beta of 3.
So as I mentioned, so if you're making plots for a paper, you probably want to use like Saracen. If you want to do like just these kind of plots in Python, but I mean, SPH is fine. Probably the one thing if you make a plot for a paper, which I'm allowed to touch this.
Yeah, go ahead.
Is just increase the character size. So set character height. So probably I've been debating increasing this by default, but you know, something a bit bigger if you're going to put it in a paper would be better. So the sort of default mode is meant to be for like what kind of thing you would do if you're going to put a plot in paper. And if you're going to put it in a paper, what kind of format should you use? EPS?
Yeah.
Yeah, just a vector format. Yeah, don't use PNG in your paper. Yeah. Just so the text appears sharp and everything like that. But you can, so if you just want to do this kind of thing where you make a plot, Saracen's also a really nice package for doing that. What it doesn't do is this nice like interactivity. So that's what you don't get out of doing this in a Jupyter notebook or something, is you don't get the nice little clicking through and adapting and whatever else.
And Saracen is for this specifically, not.
Saracen is, so the tricky thing in SPH that's different to like visualizing other codes is we've got this business about we've got data on a bunch of points and we want to present it as a smooth field. And the way we do that is sort of related to the method because we discussed it this morning, which is you have to use the kernel to get the smooth field on the pixels. And we want to use the kernel we used in the calculation so it's all consistent. And so that's why we have a kind of special visualization tool, if you like, for SPH. which is kind of why, like I said with YT, like the dumb thing to do is like interpolate to a grid and then do grid interpolations. So some of this stuff is in YT now, I believe. I'll do that. I think that's the main problem. So yeah, Splash is probably more like these days. It's been around for a while, but it's kind of more useful for like for the interactive exploration of your simulation. And if you want to people like making plots in Python these days, which is Saracen is probably your go-to for that. And obviously, if you want to just drag the data into Python and do some kind of analysis on it, Splash does a lot of things.
Go ahead. No, keep.
I mean, a few people were asking, so if you did, in the worst case, want to just interpolate your stuff to a grid, sometimes it's necessary. How would I do that? Well, let's take snapshot number 10. I would just do splash the grid. Yeah. So place it to a grid for you. I never do that. But sometimes so we're having a conversation with a few people about they've got particle data and they want to get it on a grid for some other reason. Splash the grid also has that, uses the same interpolation routine as we use in.
What would negative H mean?
Negative H. That's a negative H.
Just in the warning.
It means we've got some accreted particles.
Oh.
So we set H to negative on particles that are swallowed.
Okay.
Just to tag that they've been swallowed.
Oh.
Mass not conserved.
That's because my limits are not the whole particle distribution. So it's just cropping it's not, obviously my grid is not including all of the particles.
Oh, right.
So that's normal. But if I did go to snapshot number 10. So obviously you can just give one snapshot on the command line, but that just doesn't give it the option to skim through to the next one. Actually, something that's done we teach how do viscous accretion disks work. I mean, where does the angular momentum go? It's conserved. So where does it go?
In and out?
In and out, mostly out. Yep, mass goes in, angular momentum goes out. So if you adapt at some late time, you see the particles a long way away. So we're not that far away here. But you'll see the longer you run it for, the more particles you're going to get very large distances. You're going to get a few little tail of material that goes large distance. So we see the sun here.
Is that physical to have just a few really far out?
Well, in the picture of viscous accretion, you're removing.
Just send one to infinity.
You send one guy to infinity and it carries away a lot of infinity. Yeah. Well, just another example while we're here. So things you should check. A little sketch actually. Let's see. This everyone.ev. So this has your total energy. So total energy won't be conserved because we're just imposing a temperature on this disk. Or got cooled.
Yeah.
So, but what should be conserved is total angular momentum, for example. And this is pretty good. We're in the fourth digit here. In terms of angular momentum conservation. I believe F works as well as a flip option. So you can flip the column in each time. So total linear momentum, you can see we're sort of at the 10 to the minus 8-ish level, total linear momentum. This is with self-gravity, so probably the errors here is coming from the tree code, not exactly being symmetric in the gravity calculation, but it's pretty small for that.
There's one thing I forgot actually. I told everyone we would plot tumor Q, and I completely forgot to show you how to plot it. Right. So move this back up very, very quickly. If we let me bring in. Okay. Right. If you just, what you can do is you can actually change coordinates in Splash, right? So if you, in this menu, if you go into the options menu, change coordinate system is what you need, number 7, right? So 07, and then switch to the cylindrical coordinate system. We're thinking about disks, so we want to think about the cylindrical side of things. And very, very helpfully, Daniel has put in your TUMRA-Q parameter. So this, we're now in R, phi, and Z, right? So if you now plot 17 against 1, that will be your TUMRA parameter against radius. And how did that happen?
You probably can't go back to Hollywood mode. Just delete your default files.
My default, okay.
If you just want to use a different set of default files, you just use -p on command line as well.
Okay, right, so 07, right, we're in the, we're going into the cylindrical coordinate system, and then 17 is the TUMRA parameter against radius, and here we go. At the very, very inner edge, it's going to do all sorts of funny things. So I'm just going to need to zoom in. And this is what, see, we might have to zoom in quite a bit. There we go. Okay, so so you can see that basically it goes out to, here's 0, here's 1. So at the very outer edge of your disk, it's actually a TUMRA-Q of 1, right? So remember, TUMRA-Q of less than 1.7 is when you start to get spirals forming. So you don't see spirals at the very beginning. And over time, let me sort of go through this.
So everyone should press S. That's fine. Oh no, so
no, what's going on?
I think it's having problems because so what I didn't explain is actually it's very important. You'll notice if you type ls-l in the directory that every temp file, actually can we go back, can we just jump back out? So have a look in the .in file.
.in file.
Is important, but I'm not going to change the default. So by default, every tenth file is what we call a full dump. A full dump is a restart file. It has all the information in it that you need to restart the calculation. But if you just did this every time you wanted a snapshot, you fill our disk quota very quickly, and we have a shared disk quota on our group, and it annoys everyone when the disk is full because you can't run anything. So like the number one thing is you don't want to like fill the disk too quickly. So if you type ls-l, so what's a small dump? So a small dump is a dump with, doesn't have velocities and temperatures in it. You can see the file sizes here. So these are like, what is that, 2 gigs? And this is 400 megabytes. So this is like a factor of 8 smaller. Did I divide it correctly? No, I didn't.
5.
Yeah, so it's written in single precision. It doesn't have velocities and temperature in it. It's just designed to make pretty movies with, but you can't restart from it. So that's the reason if you try to visualize those and you're using temperature or velocity, it's going to just give you blanks. So the way to do it is to plug only anything ending in 0 when you give the file list if you're going to use temperatures or velocities. Or you can set that n full dump equal 1. Use with caution because everyone will hate you when you fill your disk.
And you need your temperature to plot Q, and that is why that was.
So go back to your command line one. So what I was doing.
Okay, so.
So just if you just put a 0 after the star, that's going to get everything that ends in 0, which is all the
Okay, so back to the cylindrical menu. Here we go. 2, and then we've got our TUMRA parameter, it's number 17, against 1. Oh, it does that by default. Oh, this is just asking if we want to, you need to have a central mass, and so it's just kind of saying, well, do you want to stick to the default or do you want to change it to something else? We'll just stick to the default, and then I'm going to zoom back into here again. Here we go. Okay, so If I just save that, and then we should, over time, we'll see that that actually changes because much of the disk has become unstable. So here's your tumor Q of 1. And actually this one ends up fragmenting, which is why it's sort of kind of really, really down below. That I think is pretty much it. The only other thing, if you remember, Daniel's movie was a movie of the disk and the tumor Q. That again comes in this multiplot menu, so you can actually, before, I think you had your x-axis was always the same when you did the shock test. That was the x-axis was always x. In this case, we don't want the x-axis to be the same. On the left-hand side, remember Daniel's movie was y against x, whereas on the right-hand side, we want tumor Q against R. So you just need to go through a few additional steps, which I will leave you to do in your own time. Yeah.
Hands up if you got a movie. Hands up when it's ready. It's pretty happy customers. So Splash pretty much does everything. Like it probably makes copy if you give the minus copy flag.
No.
I really like so there's lots of things in there that you can muck around with. The text interface is a bit funky, but yeah, it's pretty much the same procedure. Any simulation you're running with Phantom that we just did. Lots of applications that we've done are pretty out of the box. So I think like go ahead and muck around with. So we're mucking around with another one Friday week, which is an MHD simulation with like launching a jet from a young star. Haven't checked that one yet, but it should work.
I think that's pretty much it, really. Yeah. Happy to just chat with people if you've got any specific queries, or I'm around tomorrow as well. But that's it. Then I'm not around after that. But Daniel's here.
I guess yeah. If there's any last questions,
yeah. No, we're all good. Okay.